And there you go. There's my screen, and I'm gonna start my packet tracer. And inside of our packet tracer, what we saw yesterday was actually different, I would say, topologies. If I open up one of the topology that we did, was this. So this was pretty normal topology that we actually had. And we saw how IP addresses actually can be configured by using DHCP as well. There you go. I have saved the configuration, or I have saved the topology, which actually results in the saving configuration as well. And when I actually try to send traffic from here to here, first time it fails, second time failed. The routing table must or might be exchanged. Yeah, there you go. So it's successful. And then we added up into that topology yesterday, and we created multiple such routers. We had 4 different routers, 4 different switches, and the endpoints were also different over there. Correct? And when we try to send this particular, or when we try to use the configuration like that, then you need to add multiple static routes inside your routing table. Now, if I compare that, there are almost 10 to 15 static route that needs to be added onto the device. So how do you like solve that particular problem from there? So what you do, instead of adding these multiple routes, you make use of something called default static route. Makes sense? So if I have multiple such routes, be it like router 3, router 4, and so, and then there are, let's make up a topology that looks actually like that. So if I place these 2 routers, and if I place some other switches over here, and then if I say the PC is gonna be like this, and then the connections are gonna be connected in this way. This is what the topology was, right? When we actually worked. Okay. So we need to make it over here, because the router that we used was not PT router, so it doesn't have the serial ports. That's why we need to use this one over here, like this. And then we connect all these devices together. And then the networks that we actually used was 1.0. We had 2.0 here. Then we had 3.0. We had 4.0. We had 5.0. Then we had 6.0, and we had 7.0. 192.168, of course. This was kind of the scenario that we actually had. Now we saw the number of, I would say, routes that you will need to add over here was about 5 routes, right? And then the number of static route that you needed to add on R4 was again 5 routes. And then there were around 4 routes that needed to be added over here. But let's consider that both of these routers are actually something you can say called the edge routers of your device, and you have different networks that are situated, and you need to reach out to multiple static routes that are going out there. So what I'll do, I'll configure the basic IPs in just 2 minutes, and then we'll look at this scenario how it should be worked. So when I go into R1, I can go into configure terminal, and I can say hostname R1, interface FA0/0, no shutdown, IP address 192.168.1.1 along with the subnet mask, and IP DHCP pool A, network 192.168.1.0 along with the subnet mask, and a default router of 192.168.1.1. And then you can take an exit and say interface SE2/0, say no shutdown, IP address 192.168.5.1 along with the subnet mask. Correct? Then after that, we went on to R2, and then in R2, we specify the IP config like that, saying no enable configure terminal interface, you can say host name R2 interface FA0/0 no shutdown IP address 192.168.2.1 along with the subnet mask, and then IP DHCP pool B network 192.168.2.0 along with the subnet mask, and then the default hyphen router 192.168.2.1, and then we switch the interface to SE2/0, then we say no shutdown and IP address 192.168.5.2 along with the subnet mask, and then we change the interface to SE3/0, no shutdown and IP address 192.168.6.1 along with the subnet mask. That is exactly what the configuration that we did onto our R2, and you can verify that the interfaces are configured FE0/0, SE2/0, SE3/0. And then we went on to, you can say R3, and we said no here, enable configure terminal interface FA0/0 no shutdown IP address 192.168.3.1 along with the subnet mask, and IP DHCP pool C network 192.168.3.0 along with the subnet mask, and default hyphen router 3.1, and interface SE2/0 no shutdown IP address 192.168.3.6.2, interface SE3/0 no shut IP address 687.1. There you go, right? And you can verify R3 also is working pretty good. And then lastly, we actually went on R4, and then we say enable conf hostname R4 interface FA0/0 no shutdown, and then IP address 192.168.4.1 along with the subnet mask, and then IP DHCP pool D network 192.168.4.0 along with the subnet mask, and then we say default hyphen router 192.168.4.1 interface SE2/0 no shutdown IP address 192.168.7.2 along with the subnet mask, and that is all that we needed to do. So this was how the configuration was actually done yesterday, right? I just gave you a quick review there so that you can relate to that configuration that we did. And now if we see, you see the number of directly connected routes that you have here are around like 2 routes, because if I go on to R1 and if I say do show, or if I say, so here's another thing, okay? When you use, I would say the show commands onto the enable mode, you can directly use them over here. But if you are in global config mode, like configure terminal, and you want to execute like show command over here, so what you need to do, because it's frustrating to go back and forth every time you want to use a show command. So what you can do, you can just say do show IP route. And when you have do show IP route, you can actually also see. So before every show command, you just need to add do if you want to execute that command into global config. So when I say do show IP route, then you can see that these two are the directly connected networks that we have here, right? And then if we look at the other routes, you can see on router 2 and router 3, you have 3 routes connected, 2, 5, and 6. On router 3, we have a node. Yeah, I'll rename that to R3, and we say do show IP route. Yeah, you cannot use the autofill feature. Yeah, that's correct. And then you have this 3, 6, and 7 over here. And then after that, if I say do show IP route here, you have 2 networks. Now see, when you have number of networks that needs to be added more than like the desired value, then what you can do. So when we actually talk about something called static default routing. So what we do in static default routing is you don't need to add any specific routes into your routing table. There is just one route that you actually need to add. Okay, and that particular route acts as the default route. And how you add it? You basically add that particular route by saying IP space route 00, because if you check, there is just one route over here. So you say IP space route 0000 space 0000 space, you specify the SE2/0, which is the interface there. Make sense? Now when I hit the enter button over here, then you can check do show IP route, and it says that my static default route has been added over here. Because when you see, it is there is not just S with the new route that we have added, it is S and a star sign, or S and an asterisk. So this indicates that it's a default route. And what does this default route means? That whenever there is going to be any traffic that is coming up to this R1, and if R1 doesn't find the destination information into its routing table, then it's going to consider forwarding the traffic onto the interface that is there with the static default route. Make sense? So if there is anything that comes up to the router and router doesn't know about the destination, then it's going to forward that traffic on SE2/0, because that is what we have told the router by implementing static default route, that if there is any unknown, then forward that traffic to serial 2/0. Make sense? So when I specify that this information over here, and on R2 I can also specify the same over here, IP route 0000 and SE2/0, and take in view over there, do show IP route. There you go. There is also static default route that has been added. Make sense? Now, what about R2 and R3? Because if I say that we have two exit interfaces, right? So if I go ahead and if I say something like on R2 that IP route 0000 and say SE2/0 as well, and then we say SE3/0 as well, because we have two exit interfaces, right? Now, when I check my routing table, what do you see here? There is a static default route that has been added, which has exit interface as SE2/0 as well and SE3/0 as well. So what will happen in this particular case? Any guesses? What will happen over here is, you see, I will try to send traffic now by getting IP address onto these devices. There you go. And I'll also get the IP address configured onto this PC and these PCs. Get that? Now what's gonna happen here is when I try to send traffic, probably the first traffic is gonna go failed. But yeah, if I resend that traffic, successful. And now if I try to send traffic, failed. And if I again try to send the traffic, successful. You understand what's happening here? If I try to send traffic, failed. If I again try to send traffic, successful. So what's happening is that half of the packet the router is sending on this interface, and half of the packet the router is sending on this interface, because it has two exit points, right? So it does something that we call as load balancing. And how does it balance the load? It forwards some of the traffic on the first interface and some of the traffic on the other interface. Do you understand what I'm trying to say here? Yes, it forwards the traffic, like by doing the load balancing between the interfaces that you have. Makes sense? So that's why it is not advised at all to use a static routing when you have multiple exit interfaces on your router. And when you have such scenario that you have multiple exit interfaces, then the only way to implement static routing is implement static routing for the less amount of network that you want to add, and implement static default on the interface where there are more number of networks that are situated. Meaning, if I say SE2/0, then my SE2/0 is just going to reach out to one static route. But if my SE3/0, you can see that this has three indirectly connected networks directing over here. So what I'll do in this case, I will go back and I will remove the static routes that I've added for 2/0. So I'll say no IP route, and then you can see do show IP route. There you go. So you just have one static route over here, and then I will add a manual route for 1.0. And you can check that now. Do show IP route. There you go. There is a static route for 1.0 and a default route facing towards SE3/0. So now if I try to send traffic between here to here, successful, 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 successful. Make sense? Yes, Amar, that's correct. So if you shut down SE3/0, the route will no longer be available into the routing table. And that's why there will just be one route. So that will kind of solve the problem in one way. But then again, when you add this on R2, we will do the same thing. We have more number of networks to be added that faces towards SE2/0. So we'll implement static default on this interface, and we will implement static on the other interface. So we're gonna go onto the router, and then we say IP route 0000 SE2/0, and then we are gonna implement manual routing for the network that is facing towards 3/0 by saying like this. Makes sense what we're talking about? And then like that, I will also, yeah, now my complete network must be converged, and you can see it over here and over here as well. Okay, there is no IP address. Whenever you get this error, it means that there is no IP address that is configured onto the endpoint. So you can go onto this PC and you can say DHCP there, and there you go. And then after that, you can configure DHCP on this as well, and then DHCP there as well, and then DHCP on this as well. And when I do that and try to send traffic from here to here, the first packet fails out, but then successful. Then from here to here, first packet fails out, successful. So that's how you can like make the communication happen there. So on first routing, on first router and last router, we just have a static route and no like static default route and no static route. But on R2 and R3, we have a mixture of static and static default. Do you guys understand what we're talking about and how static routing works now, or static default works now? Perfect. So go ahead, try doing the modification into yesterday's topology that you did, and see if you're good with the configuration that we did. All right. I hope you are done with the lab. So we can move on with the next topic. So do you understand the concept of static routing? We talked about static and default. Well, there is nothing much to understand what goes into default, because default routing is used in order to, so there's just one logic that you can use this. Whenever you have a router that just has one exit point, then it's better to implement default routing, because the traffic doesn't need to be filtered out to different like, so that the router can decide on which interface does it actually need to forward that? So if you know already that where to forward that particular traffic, and there's just one exit point, like this router. So this router doesn't have any choice of forwarding it on some other interface, right? Because it only is connected to one interface there. So that's why we implement default routing. So instead of adding all the other routes, you can just put a route there that says 0000, which will kind of implement the static default route. All right. Then there is another small concept that you actually need to look into, which is called as floating or floating static route. We have something called floating static route. What is one-time default? I don't know what's one-time default. So we're going to discuss about something called floating default route. Now here's the thing. You might have redundancy that is implemented in your network. For example, if router 1 connects to router 2, not by using just single interface over here, but by using multiple interfaces. So what in that particular case? Yeah, we did this default routing on every router. So over here, I'm designing a scenario where you have one more router in place. And this router actually is connected to both, you can consider it to here as well and to here as well. Okay, which means let's consider something that this particular router has 8.0 and 9.0 network. Okay, now you can see that the type of cable that they have that they're connected with is like this is serial link and this is fast Ethernet link, because the R3 doesn't have like or R2 doesn't have any more serial interfaces. That's why the router is actually using the fast Ethernet network here. Makes sense. Now when I consider the same, let's configure the IP addresses over here, and I will go on to R1 and configure 8.1 onto the SE3/0 over there. So I'm going to go on R1 and say enable configure terminal interface SE3/0, no shutdown, IP address 192.168, then 8.1 along with the subnet mask. And then I go into R2 or this new router, which is, let's say, R5, enable configure terminal, and then go to interface SE2/0. I'm going to configure hostname as R5, and then I'm going to say interface SE2/0, say no shutdown, and then IP address 192.168.8.2. And along with that, I'm going to give the subnet mask, and then I'll also turn on the interface, which is FA0/0, no shutdown, and IP address 192.168.9.1 along with the subnet mask. Okay, and then I'm gonna go on to the FA1/0 on this router, which is R2. Enable configure terminal interface FA1/0, no shutdown, and IP address 192.168.9.2 along with the subnet mask, and take an exit. So you see, by configuring these addresses, what we have done. So we have created a scenario where we can see that there is a redundancy implemented between the connection of R1 and R2, which means that if these two networks or the computers of these two networks want to communicate together, then They can go via directly between R1 and R2, or they can go from, or they can go directly over there, or they can go with the help of this R5 that has been placed here. Now here's the thing. So if I look at my static routing table, configure terminal, and do show, okay, sorry, yeah, do show IP route. There is a static default route which says whenever there is any unknown network, then forward the traffic via SE2/0, which means if there is anything apart from that, or which, like, let's say that there is something, the network goes down, the primary link goes down, then what happens? Can anyone tell me? If I go onto the router over here and I say interface SE2/0 and say shut down, now what? If I check my routing table now, there is no static route that is available. So even though my alternate interface is up and the traffic needs to go by using this via this R5, still there is no route there for that particular network to be sent via the other way. And why is that? Can anyone tell me that? Because the traffic is not declared or the route is not declared. Okay, so here's the thing. What should I do? Shall I declare a static route or shall I declare a default route? Okay, let's go and say I'll declare a static route, and I will say IP route. Which route should I declare? For 192.168.2.0, right? And then I say 255.255.255.0 and say SE3/0 and take an exit. And then if I say conft and do show IP route, there you go. 2.0 has been added now. Do you think the traffic will go now? If I say from here to here, what do you think? The traffic should travel? No, of course. And why is that? Because we also need to add 9.0. Is it so? Okay. So I'll go on R1 and I'll say IP route 192.168.9.0 space 255.255.255.0 and SE3/0, right? And then after that, I go over here and on this router, we need to add 8.0 as well. So I'll say IP route 192.168.8.0 2550, oops, and say FA1/0. And I will also add a route that goes on to here by saying 1.0. And if I check now, do show IP route, there you go. You have the static route for 1.0 and you have a static route for 8.0. Still, the middle router doesn't know about any of that particular route, because if I check do show IP route here, it says I only know about 8 and I only know about 2, or 8 and 9. So this also needs to know about 1 and 2. So I say IP route 192.168.1.0 255.255.255.0 SE2/0, and then I say IP route 192.168.2.0 255.255.255.0 SE, oh sorry, FA0/0. Correct? And when I say do show or show IP route now, then this router also knows about both the routes now. Now, when I try to send traffic from here to here, then it says failed, try again, successful. Make sense? So you are able to send traffic now between this PC to this PC. And the traffic is actually going via the other route. And if I check that, I can go into the command prompt of the PC and I can try sending tracer 192.168.2.2, and there you go. It's going via these routes. So it's going towards 1.1 first, then it's going towards 8.2, then it's going towards 9.2, and then gets delivered to 2.2. So it specifies that I'm going via this particular route. And if I check it into my routing table, do show IP route, then you can see that's the only route that is available. Do you understand this scenario? Then we will talk about the further thing. Okay. Then what we are going to do now, I will bring this other interface up. So I'll say interface SE2/0, and I'll say no shutdown. Now the interface is up. Now what's going to happen? Which route will be preferred? Is it going to prefer the SE2/0 route, or is it going to prefer the SE3/0 route? We're talking about 5.0 network will get preferred. Why so? Because it has shortest path. Okay, because it's directly connected there. But 8.0 also is directly connected. Or you say because that's the default route. Let's see. If I look over here. So yeah, you guys are saying that the preferred route will be the 5.0, right? Let's check. If I go now and try to send traffic, it's still the same. It is still going through 8.2 network. And if I look into my routing table and say do show IP route here, there you go. Both the routes are there. You have a static route going towards 2.0, and you have a default static that goes towards SE2/0. And even though we have both the routes here, the one that is being preferred is the other one. So you see, if you consider something that says I would say the link that you have over here with the serial one is connected with the shortest distance possible. And the link that is connected the other way via R5 has a longer distance to cover. And even though when we look at over here, then there is something called administrative distance. And when we look at this administrative distance, which is often referred as AD value, then every route over here or every protocol does have some administrative distance value that is written by default. And this administrative distance value, the static has an administrative distance value of 1, and the default route has an administrative distance value of 254. So when a router needs to decide that which route needs to be preferred, then the router will look at the protocol's administrative distance value, and it will choose the one that has lesser administrative distance value. Make sense? So it doesn't look at how far is it or how better it is to reach out to the destination, but it will actually consider that particular value to be chosen. And that's why, as the longer route is being connected by using static and the shorter route is being connected by using default, this is exactly why it is actually choosing a route that has lesser AD value, and that's why it's going this way. Do you understand it? Sounds good, right? This is how networking becomes fun as we go deeper into it and compare it with the scenario. Yeah, it does not care about the lesser distance. The consideration of lesser distance comes later when there is no competition between the type of protocol that the router needs to choose. Now, this is something you can say the preference or the route preference of static routing. Now, as I was talking about, that we are going to see something that is called as floating static route. This floating static route is something you can say that what if I remove the static default route that is going over here. So what I'll do, if you can look at that in my routing table, 1.0 is learned by static itself. Okay, and over here what I'll do, I'll remove the static route. Do show IP route. And I'll remove this default route. No IP route 0000. And then I say SE2/0. And I will add another static route, IP route 192.168. Now here's the thing. Okay, before removing that particular route, I will add that static route again. Okay. There is some more thing that I need to explain you. If we go deeper into that, SE2/0, take an exit, show IP route. You see the static route is back again. And if we try looking at which route is it going to prefer, there you go. It's still preferring the next route, right? Or it's still preferring a route that actually is connected via the 8.0. Now, over here, we don't have a static default route that goes out on SE2/0. We just have added the information about 1.0 network on R2 by using static route itself, not default. So when I use this information and look at the command prompt, you see telnet, you see tracert 192.168.1.2. This particular route is using something called, okay, that's a false information. This particular route also is using the other way or the other route to be sent over there. And when you have this particular route over here, you can see that the routing, if you check the routing table over here, then R2 has an understanding that a 1.0 can be reachable via FA1/0 as well and SE2/0 as well. You understand that? But which route is it going to use all the time? It will only use the route that is connected to FA0/0 because that is prioritized. Now what I'm going to do over here is I'm going to remove this particular route. Go into the conf team. I say no IP route 0000 0000 SE2/0. Just a minute. Yeah, so as I have removed this route, what I'm gonna do, I'm gonna add the route again. Say IP route 192.168.2.0 255.255.255.0 SE2/0. And then I say do show IP route. There you go. Now what do you see? For 2.0, there are two interfaces that I have. One is connected via SE3/0 and the other one is connected via SE2/0. Make sense? Now when I see that which route is my traffic going to be forwarded accordingly, it is still going by using the other way. It is reaching out to first, it is reaching out over there via 5.2 itself. Okay. However, it's showing you that it's going through 9.2. But what happens is it's reaching out over there on the router, then it's forwarding to some other interface and then some other interface and then to the destination. So internal switching as well works into router. That's none of our concern as of now. But as of now, what you can see is both of them are equal now. There is no default route. So you can say there is just static route. And the router needs to decide which static route does it needs to use in order to forward the traffic. Should it forward the traffic by using SE2/0 or should it forward the traffic by using SE3/0? And currently, it is forwarding the traffic by using the 2/0, which is the shorter path. Do you understand this? Yes, no? Perfect. Now, when I look over here into the perspective of R2, and when I try to send the traffic, this traffic is also being delivered by using uh, 2.1 and then on this interface and then over here. So both of them, they are basically using the first interface that they know about in their static routing. You see, if I look at the route, it is actually using this particular route, and there is no load balancing that is happening. Okay, so when I say that the one of the interface goes down, the other one will come up, and when the other one will come up, then that is going to be the preferred interface. So it's always the first interface that you have inside the routing table. But this is not how we want it to behave. We want it to behave in a way that when there is the shortest path that is always available, then always use that no matter what. And only use the other path as the backup one. So what we are gonna do, there is something called metric. And metric can actually be set, and the route having lesser metric will be preferred. Okay, so you can also calculate something called metric with the help of a command along while while you add the route into your routing table. And how you do that? So what I'm gonna do, as both of these are preferred routes equally, I'm gonna remove this particular route 192.168.2.0 space 255.255.255.0, and if I see do show IP route, there you go, all the routes has been removed. And now if I say IP route, I want to add a route for 2.0 along with subnet mask, and the first interface is SE2/0. With that, I can specify that what should be the distance metric, and I can specify the distance metric between 1 to 255, any value that I want. So I'm gonna say 10 over here for the first route, and for the next route, which is going to be reachable on the same network but with SE3/0, I'm gonna say the metric is 20. And then I'm gonna do the same thing over here as well, that I do have a route that says do show IP route, and I'm gonna remove that route 192.168.1.0. No, metric is different than administrative distance. I'll explain that just a minute. 0 FA1/0. Oh, sorry. Yeah, and then I'm gonna add IP route 192.168.1.0 facing towards SE2/0 with the metric 10 and facing towards FA1/0 with metric 20. Now, as we have added these two routes, what we are saying over here, that we are specifying a metric value with the route that we are adding. So with the first route, we specified a metric value of 10, and with the second route we specified a metric value of 20, and this we followed on both the sides. So when you have such thing in your network, what it's gonna do, whenever you always have the SE2/0 up, then it will always forward the traffic by using the first interface, which has lesser metric value. And then if you consider that if this link goes down, then and then only the backup link will be used. Make sense? Because if I try sending traffic now, you see the traffic will always go like that. Okay? And if I go over here and check the same, there you go. That's how the metric is actually going. And now if I say, gosh, there you go. Now if I say that my interface SE2/0 goes down and I say shut down. Now what happens? When I try to send traffic now, You see, it's using the other interface in order to forward the traffic. Yeah, the metric can actually be valued, or you can specify the metric by considering that which route do you want to prefer and which route do you want to use as backup. Based on that, you can create a metric value in static routing only, like this. So as you can see, when the first route went off, then and then only the second route is being used. Okay. But if you do not use metric value, and if the primary route comes back again, and there is no metric that has been calculated for that particular route or specified for that route, even then, the router will continue using the current route that it's gonna use, which is the longer distance one. Do you understand what I'm saying? If you do not use metric to specify the priority of the route that you want to use, then the router keeps on using the current route that it's working according to. So redundancy is there, which means that without metric being specified for those routes, when the primary route goes down, then the secondary route it will be up, and it will solve the purpose of forwarding the traffic. But when the primary comes back again or comes back up, even then as well, the router is going to consider using the secondary route continuously over there. Make sense what I'm saying? Exactly. And that's what I'm going to demonstrate, that as of now we have configured a metric with us. And when I try to forward traffic, you see it's going the other way. But now if I go onto the router and say no shutdown, okay, the interface is up now, you can see that. And then if I try sending traffic now, you see it's back to the primary route now. Make sense to you what I'm talking about? This is something that we call as floating static, which means the route actually floats and depends on the metric that which route needs to be used at what time. Interesting concept, right? But yeah, this is how actually static route is used, and these are the variations of static routes that are available. So go ahead, try this scenario and see if it works for you. Okay, there is no modification of commands, there is just something that you add the value, the metric value with yourself, with your route. But try see variations of this, try to create an alternate route and see if you keep one as default and the other one as static, what happens. Then turn both of them to static and then implement floating static route. Make sense? Okay, there is no specific command that we have used, just normal things. So go ahead, try this thing, let me know when you're done. All right, let's move on to the next thing then, as you all are good with the config. So the next topic that we want to explore is called as VLSM, which stands for Variable Length Subnet Mask. And in order to do that, let me first explain that to you, what this VLSM is gonna mean to us. And the concept that we're going to discuss about is VLSM, which stands for Variable Length Subnet Mask. Right? So you're gonna take, I would say, a scenario where you have four routers. You have this router one, then you have this router two, then you have, let's say, this router three, and you have this router four. And each of this router has a local area network. So you can say that this router has couple of PCs connected with it with a switch. Then you have this another router which has another set of, I would say, PCs connected over here. And then this R4 also has set of PCs, and this also has set of PCs connected. Make sense? Each of this network is dedicated to some department of your enterprise lab. So you can say that the network number one over here is dedicated to sales department. Then the network number two is dedicated to marketing department. The network number three is dedicated to HR department, and network number four is dedicated to admin department. Make sense? And if we look at the number of employees that are going to be connected in this network, are the sales is going to have 120 users. Then marketing is going to have around 60 users. HR is going to have 30 users, and admin staff is going to have around 10 users that are going to be connected. And when you have such scenario, then you can see that the R1 will be connected with R2, R2 will be connected with R3, R3 will be connected with R4, and R4 will be connected again to R1. So this is how the scenario is going to be like. And then you can consider that the only network that you have been given by your network admin is 192.168.1.0/24. You need to segment the network, or you need to create subnetting according to the requirement that we have. So you see, the only thing that you need to notify here is the length of the users in each of this network is different. The first network requires 120 users, the second network requires 60 users, the third network requires 30 users, and the fourth network requires 10 users. So we cannot like go ahead and use 1.0 here, or 2.0 here, 3.0 and 4.0 here like that. It's not possible. So what we need to do is we need to create subnetting according to the range of each network that you go. So the biggest rule, however, in VLSM, do you understand what we're gonna have here? Please respond in chat. We're gonna have networks with different number of hosts. Exactly. Now the only golden rule that you need to follow in VLSM is biggest network biggest network comes first over here, which means you create subnetting for 120 at number 1, then you go to the smaller network number 2, then you go to even smaller network, and then you go to even smaller network. Make sense? So this is the biggest rule that you need to follow, or the golden rule that you need to follow, which means that the biggest network or in size will be subnetted first. And the number of network that you come up with doesn't really matter over here. Okay, the number of network that you might have for the first network might be different, then over here it might be different, over here it might be different, and different over here as well. So how we do that? For such scenario, what we are going to do, we are going to specify over here. So what's the requirement of our network number one? The network number one is working in a way that you can say that the number of hosts, or you can say it is for sales, right? So sales department, and the number of hosts that you require is 120. So if I write down my master formula, which is 128, 64, 32, 16, 8, 4, 2, and 1. This is the formula that we use, and then we figure out number of network first, then you go with number of host, then you go with subnet mask, and then you go with ranges, right? So if you figure out number of network, then in VLSM, what you need to go ahead and how you need to go ahead is you first will figure out number of hosts. So as this number of hosts required is 120 for the first network, what you choose is 128 as the nearest value, and which sits at 2 to the power 7. Okay, so what you're gonna do, you are gonna keep 7 bits as off. That's why you will figure out first how many bits needs to be off. That will give you enough number of hosts, and that's 128. And out of, like, as we are using 192.168.1.0/24, what's the, like, how many bits are reserved for host? Only 8 bits, right? Out of that, you need to keep 7 bits, the last 7 bits as off, and only the first bit will be on. That will give you two networks. And as you figure out that you're gonna have one bit as on, that's why it goes from /24 to /25 for the first network. And the /25 has a subnet mask of 255.255.255.128. That is what the subnet mask is. Yeah, you can see over here, Nikin, that when you have this VLSM scenario here, it means that you need to implement subnetting in a way that the range of, or the length of the network for every network is going to be different here. And that's why when you consider using subnetting, then for this particular scenario, we have 120 users that can be connected with this switch. I've just drawn three lines, but you can have around 120 users that are going to be connected. So for that, we need to use a single subnet, which is /24 by default, which gives you around three, I would say, three network prefixes and one host prefixes. So this one host prefix contains 8 bits, right? And these 8 bits will be the number of host particles. But out of that, we just need to keep 7 bits, because when we see the number of hosts is 120, then from the master formula, the nearest value that comes, or that we can come up with for a network having the host particles is 128. And for that, we are going to keep 7 bits as off, because 128 means 2 to the power 7, if you know. And as you figure out that 128 means 2 to the power 7, this value comes over here into number of hosts. And if you keep 7 bits as off, which means if I draw this like /24 by default into binary, this is how it's going to look like. Right? This is what the basic thing is. Now, out of these 8 bits, because this is network, this is network, this is network, and this is host for /24. And out of these 8 bits, what we are going to do, we are only going to reserve last 7 bits, okay, as 0 for host. And then this first bit from the last octet will become to 1. So that entirely becomes a /25 network, 888 and 1. So it becomes 192.168.1.0/25 network. That gives you the subnet mask of this. And when you come up with the ranges, then that what all are going to be the ranges that are going to be used, then you can say that the ranges actually will be something. The first network is going to be 192.168.1.0 to 192.168.1.127. And then the next network is going to be 192.168.1.128 to 192.168.1.255. You understand that? This is how we are going to come up with two networks, each having 128 as the number of hosts there. Do you understand it? Now, out of these two networks, we are only going to use the first network. Okay, so this network will be dedicated to the first one, which is 192.168.1.0 to 192.168.1.127/25. Then the second network that we have, which is this, will be again subnetted to the next requirement. So the next department that we have is marketing. And inside this marketing department, the number of host requirement that you have is 60 users. So we again calculate number of network, number of host, subnet mask, and ranges. And if we come up with a value that is nearest to 60 users, then you have 64 users. You can come up with a network of 64 users, which is 2 to the power 6. Make sense? That's why the number of hosts will be 2 to the power 6, which is 64, which means you will keep last 6 bits. Out of 32 bits, you're gonna keep last 6 bits dedicated for the users, and that's why you will have a network of /26 over here. Make sense? So when you keep up like /26 for a class C network, it means you're gonna have number of network as 2 to the power 2, which is 4 networks. But this doesn't really matter over here in VLSM, because the subnet mask again can be figured out for /26 as 255.255.255.192, like this. And then the ranges are going to continue from where we left. So it's going to be 192.168.1.128 to 192.168.1.191. So that's what the network will be. Make sense? Yes, now. Right. And then the third network that you're gonna have is for HR. And in HR, the number of users are, I guess, 30 users. For that, the nearest value will be 32, which is 2 to the power 5. So number of network, number of hosts, subnet mask, and range is going to be in a way that number of hosts will be 2 to the power 5, which is going to give 32. Number of network for that will become 2 to the power 3, which is going to give 5 networks. The subnet mask is going to be 255.255.255.224, and then the range will be 192.168.1.192 to 192.168.1.223. That's going to be the next network dedicated for that. Make sense? Yeah, the network gets divided and divided, but we only use, I would say, okay, sorry. 2 to the power 3 over here will be 8. Yeah, it is 8. Correct. So we have multiple networks, but we just use the first range that is available, and then we further subnet it. Okay. So I'll write down the networks that we're going to use here. That for 16, we're going to use 192.168.1.128 to 192.168.1.191/26. And then for HR, we use 192.168.1.192 to 192.168.1.223/27. And then over here, if we look at the configuration for the admin, then the admin, which is a network, has a requirement of 10 hosts. And these 10 hosts are going to be some or the other way being used in a way that we will use 2 to the power 4, which is nearest value to it, 16 hosts. So that's why when we say NHSR, it's going to number of hosts will be 2 to the power 4. Number of network again will be 2 to the power 4, which is going to give 16 and 16 each. Then the subnet mask will be 255.255.255.240, and the range is going to be 192.168.1.200. And because 8 cannot satisfy our requirement, we cannot take 8 because the requirement is 10 hosts, right? And then 1.225 to 192 168 1.239. That's what the range will be for the last network, which is of slash 28. So we're gonna write it down over here, and we specify the fourth network is gonna start at 192.168.1.225 to 192.168.1.239 slash 28. That's how the subnet actually is gonna go. Makes sense? We just want 16 users to be configured. The last network ended at 220. Oh, okay. Sorry about that. So we're gonna start up at we're gonna start at 224. Oh, sorry. Yeah, makes sense. That's how the range is gonna be. I hope you understand that. Yes, no? Perfect. So let's go ahead and see how the configuration actually can be done for such type of configuration. So I'll share my other screen with you. You can take a screenshot of this if you want. And this is how our topology is gonna be. So I will stop sharing the screen and I will share my other screen with you. And there you go. You have this topology here. What I'm gonna do is I'm gonna power cycle on all these devices, and I'm just gonna make some modifications. Delete this, delete these links. And over here, right, these are our fast Ethernet networks, and I'm gonna use them in a way that this is our R1, that's our R2, that's our R3, and that's our R4. Okay, so I'll put this across over here like this, and then I'm gonna put it over here like this, right? So the network that we're gonna use here is the number of network doesn't simply needs to be considered over here. You can ignore that. The first network that we're gonna use here is 192.168.1.0/24, which is for sales. Okay. Then we're gonna have marketing department, which is gonna use a network that's 192.168.1.28/26. Okay, this is gonna be slash 25, right? Yeah, 25. And then you're gonna have 192.168.1.192/27, and then you're gonna have the last one as 192.168.1.224/28. That's how the config needs to be done. So I'm gonna go on each router and I'm gonna configure these networks and the FA0/0, and the DHCP config for them. So I go onto the router first, yeah, and say no, enable, configure terminal, then interface FA0/0, say no shutdown, IP address 192.168.1.1, but with the subnet mask of /25. And then I say IP DHCP pool sales and say network as 192.168.1.0, the network ID and the same subnet mask. And the default hyphen router, of course, is going to be 192.168.1.1 itself. Do you understand this config? Pretty simple. We need to use the network. We need to use the valid host IP address, the first IP, and the subnet mask of /25 here. Okay. After doing this configuration, what we're gonna do? We're going to move on to the next one. So I'll open up the R2. However, I need to rename R1 as well. So I'll say host name as R1. Yeah. Then I'll go to R2 and say no, enable conf t host name R2, and then say interface FA0/0. You can see that the R2 needs to be configured with this IP. So I say IP address 192.168.1.129 along with the subnet mask of 192, and then say IP DHCP pool B and say network 192.168.1.128 along with the subnet mask. Oh, sorry, yeah, 192. And then say default hyphen router. Okay, I'll give no shutdown as well. Interface FA0/0, no shutdown. And then IP DHCP pool B. Oh, this shouldn't have been DHCP pool B. I say no IP DHCP pool B. I'll delete that pool and say IP DHCP pool again for marketing. And then say network 192.168.1.128 along with the subnet mask of 192. And then default hyphen router 192.168.1.129. Sounds good? And then like that, you can have go to the third router, and this third router actually can be configured in a way. Enable conf t host name R3 interface FA0/0 no shutdown IP address 192.168. Yeah, IP address 192.168.1.193. Yeah, 255.255.255.224. And then say IP DHCP pool HR network 192.168.1.192 along with the subnet mask and default hyphen router as 192. Oh, sorry. And default hyphen router as 192.168.1.193 there. And take an exit. There you go. And just like that, you go on to the next router, which is this, and configure the address that says no enable configure terminal. Okay, and then interface FA0/0 no shutdown IP address 192.168.1.225 along with the subnet mask of 240, and then IP DHCP pool admin say network 192.168.1.225 along 224 as it's a network ID along with the subnet mask of 240 and default hyphen router 192.168.1.225 and take an exit and say host name is R4. There you go. All fast Ethernet configurations are done. Let's go on each PC and get the IP there. The router or the PCs might have previous IP addresses, but that's fine. Then go over here They already have got the IP addresses because the PCs were up, right? Let's check if we have the IP. There you go. From the second subnet, they have received the IP. From the, yeah, all good. Then we say on this, perfect, and then perfect, and over here as well. Yeah, that's perfect and perfect. You see, this is how the configuration actually works here, and that's how VLSN can be done. Okay, go ahead, try this fast Ethernet thing first and see if it works for you. And then I'll show you or give you a hint for for the serial configuration and the routing, and then that will kind of be acting as the assignment. But yeah, go ahead, try this configuration over here and see if it works for you. Let me know when you're done. Perfect. So as you are done configuring, I would say the fast Ethernet interfaces of all the routers that we have for the branches, and then you can see it's time to actually get to know about how we are going to make them communicate with each other. Okay, because if you, let's say, these people want to communicate with these, by default they won't because they both are into different subnets. But in order to make them communicate, we also need to connect both of, like all of these routers together in this fashion. And when you do connect them, as we have been using in the previous topologies, we used to like specify networks like, for example, 5.0 over here, 6.0, 7.0, and 8.0. And then we would say 5.1 here, 5.2 here, 6.1 here, 6.2 here, 7.1 here, 7.2 here, 8.1 here, 8.2 here, right? This is how we have been behaving with the point-to-point connectivity over there. Do you understand that? But over here, we are not, I would say, going to implement it the same way. Because what we need to do, we need to dedicate or we need to configure these networks with the help of VLSM, variable length subnet mask. And in the variable length subnet mask, you can say that the number of IPM. So how many networks do we have over here for like doing the configuration between the point to point? Can I say this is one network, this is another, that's another, and that's another? So you have 4 point-to-point networks that needs to be connected. Now, what is the requirement of point-to-point network? There is something called point-to-point subnet that we call it according to. And when we say point to point subnet, it means that the number of hosts that you want are going to be 4 now. Okay. And we say point to point subnet to something called /30. Yes, correct, Prince. So in /30, we get 4 IP addresses because we have number of hosts as 2 bits will be off there. That will give you 4 IP addresses. One of which will be the network ID and the other one would be broadcast ID. So what you're gonna do, as you are left with 16 IP addresses, right? Because we only have used till 239. So 240 to 255, these IP addresses are still vacant. And what we are gonna do, we're gonna come up with /30 networks over there, in which you're gonna get number of network, number of host, subnet, and mask and range in a way that number of hosts will be 2 to the power 2. That's gonna be 4 IP. 2 to the power 6, that's going to be 64 networks. Subnet mask is going to be 255.255.255.252, right? And the ranges will start from 192.1.240 to 192.168.1.243. This is going to be your first network out of that. And how many networks do you need as such? You need 4 networks, like 1, 2, 3, and 4. You need 4 different networks like that. So what you're gonna say, you're gonna create 4 different networks like that. The first one is 240 to 243. The second one is going to be 1.244 to 192.168.1.247. Then 192.168.1.248 to 192.168.1.250, I would say 1. And then the last network over there will be 192.168.1.253. 1.252 to 192.168.1.255. This is how you will use 4 IP addresses per network, and you will dedicate networks like you will dedicate network like, okay, I'll remove this mark here and over here. Yeah. So for the first network between the connectivity between router 1 and router 2, you will use 2, or I would say 1.0 or 1.240/30. For the second network, you will use 1.244/30. You will use 1.248/30 and 1.252/30. Do you understand that? So the first IP address of every network is network ID. The last one will be broadcast ID. So you will use the between, like the 2 IP addresses between of each network: 241, 242, 245, 246, 249, 250, 253, 254. And then you will assign those IP addresses to the serial interfaces, and that's how your IP configuration will be completed entirely. And once you're good with the configuration, then I want you guys to implement static routing over there and see if the static routing works and make everyone communicate with each other. Do you understand that? Okay. So to make this particular network work, this is going to be your assignment. Okay. And I expect you guys to complete this assignment in this, I would say, week. And then in the next week, we're going to start dynamic routing. Okay, so we'll say RIP, IGRP, OSPF, and that's going to be our motive for the next class. Sounds good? I hope, yeah, you should now. Yep, you need to figure that out. I'm not going to help you with the number of things that you have over here and so. But yeah, you guys can use Telegram for the communication over there. Okay. Well, you can reach out to me on the Telegram group itself. We have created a Telegram group, and I every day I look at it, and then if there is anything that needs to be responded there, I do respond over there. So you guys have my Telegram handle. You can reach out to me if you want anything. But then there are other guys as well that helps you if you have any question. So instead of like just me being answering to you, there are other guys as well. And when the doubts are shared commonly, then they help other people as well. So I request you guys to put up your doubts over there. Till then, I hope you enjoyed the class today, in which we talked about static routing, default routing, and floating routes and all, and then we saw how VLSM actually works. Yeah, it's about the static routing. It's about you would say default static, the floating static. We looked about how AD value plays roles, how metric plays roles in selection or influencing the routes, and then we talked about VLSM. That's what we covered today. All right, thank you so much, everyone. And yeah, do follow me on LinkedIn, do follow me on Instagram if you're there. And yeah, thank you so much. Take care of yourself. Bye bye.
If you enjoyed the content of the video, don't forget to like and share the video and subscribe to our channel.
And the section that we are going to discuss in this is routing information protocol. So there are different methods that you can actually implement routing information protocol, and this section actually comes in when we discuss about like dynamic routing. So there are two variants, right? You have a static routing and you have a dynamic routing. When we look into static routing, then you can say that there are different types in static routing that we have implemented so far, but we also have seen a type of dynamic routing. So you have static routing, in which we saw normal static routing, then we saw default static routing, and then we saw floating static, right? But if we talk about dynamic routing, Then there are multiple protocol that comes under dynamic routing. So first of all, you have routing information protocol. Then you have EIGRP, which is enhanced interior gateway routing protocol. And then you have OSPF. So when you have these routing protocols, then there are other routing protocols as well, like BGP, like ISIS, right? You might have heard about them. And there is categorization that is actually done for all of these routing protocols. Like RIP, it's called as distance vector routing protocol. EIGRP stands for enhanced. EIGRP comes under advanced distance vector routing protocol, and OSPF comes under link state routing protocol. Right? We'll be discussing about each and every protocol that we have here. But what we are going to discuss in this particular session is routing information protocol. So when we talk about routing information protocol again, then it clearly works more of how you can actually exchange routes. For example, if you have a router 1, then you have a router 2. And this router 1 has, I would say, certain connectivity of local area network like this. Okay, and then you have your network like 192.168.1.0 on here. You have 192.168.2.0 there, and you have 192.168.3.0 there. So when I look forward in order to send traffic from this network to this network, then in static routing, you actually need to add the indirectly connected network. We saw that how 1.0 will be the directly connected network to R1 and 3.0 will be the directly connected network to R1. Then we implemented a way that 2.0 actually needs to be added into the static route of R1, right? And 1.0 needs to be added into the static route of R2. But this is kind of not that scalable solution, because if you have multiple static routes, then in that particular case, you probably you probably would have yeah you probably would have seen something that if you have around 10 or 15 routers, or even more, 20, 30 or 40 or 50 routers in your environment, then in that case, adding all these routes or adding all the indirectly connected network route in your routing table is not going to be a scalable solution. So what do we do in dynamic routing, and how does dynamic routing actually work? Usually, when you have a router here, and then if you have a router there, then assume that your R1 actually knows about 4 routes. Your R1 knows about 1.0, your R1 knows about 2.0, 3.0, and 4.0. And your R2 knows about around 5.0, 6.0, 7.0, and 8.0. These are basically the directly connected networks to your routers. So in dynamic routing, you are not going to add the indirectly connected routes to your routing. What you are going to do over here is you are going to add you are going to advertise the directly connected routes to the neighbors or to the routers that are present into the topology. Make sense? And how that's going to happen? It's basically going to happen in a way that R1 is going to send a routing update, and in that routing update, it will contain all the details of the directly connected network that it has. And R2 is also going to do the same thing. R2 is going to initiate a transfer, which will also be called as a routing update. And in that routing update, it will contain all the routes that the router knows about. This is how we actually think about when we give it a thought that what is dynamic routing. Do you understand what I'm trying to say here? The meaning of dynamic routing. Perfect. So when we actually talk about this dynamic routing, then RIP is one of the protocol that we discuss about, or you can say the routing information protocol is one of the protocol that we call as distance vector protocol. Okay, and when we look about it, then you can see. So we are about to discuss how routing information protocol works. And in this routing information protocol, how it actually is going to work is you're going to have a router and you're going to have another router in your topology. And we are going to advertise the directly connected networks that are available there. But there are certain characteristics that you actually need to know that how the communication is going to work over there in terms of routing information protocol. So first of all, when we talk about routing information protocol, the very first thing is it is open standard protocol, which means if you have a device that is connected of Cisco and if you have another device that is connected of Juniper, okay, then you can actually implement routing information protocol between them, and it's not a vendor proprietary protocol. You don't need to worry about which devices are you connecting or does the are the vendors of those particular devices are same or not. Since this is an open standard protocol, you can implement routing information protocol in almost every device that is available there. Make sense? Then after that, you can say that when we actually give it a thought, the second you can say characteristics of your RIP is it is classless routing protocol. Okay, it is classless routing protocol. And what does this mean? It means that if you have a network that is created of /28, let's say, and then you have a /29 network here and a /30 network here. So you can actually advertise these /28 and /30 and /29 network inside the RIP, because RIP or routing information protocol had two versions. It had version 1 and version 2. Version 1 was only supporting classful routing, like you can say classful routing, which means you can only advertise your network if the networks are of /8, /16 and /24. You understand that? That was one of the limitations there. And if you talk about V2, then you can advertise almost every network that is available there. Be it /16, be it /18, be it /29, or be it /30, or almost any network. Okay, you don't need to really be worried about how you can actually do that. So, as I told you, that the second characteristics of our routing information protocol is you can actually uh, advertise your networks even if they are of classless nature, which means if the networks are made up of /28, /29, and not the default subnets, they are not following the default subnets. That's one of the second characteristics that you have. Then the third characteristics that you have here is what you can do with I can say routing information protocol is you can actually advertise your networks, or you can like advertise your networks based on the routing updates, which means that every 30 seconds your router can actually advertise a routing update, which means if you have a routing table that actually contains around 10 routes, then those 10 routes will be advertised on a multicast address every 30 seconds. Okay, and these advertisements are going to be made into that particular router, and then there the routers will get to know about those routes there. This is how it's going to work there. Makes sense? Now, what we will do, we will try to create a network and we will try to see how the advertisements are done and how the communication actually happens with the help of this routing information protocol, and see how it works. Okay, let me just clear this particular screen here and then I'll demonstrate to you guys that how we can make this work. There you go. If you can see my screen now. So we are going to drag a couple of routers here. Let's say this PT router here and here. And then I am going to drag another router here and here, and then another over here. And then I'm going to connect them together like this. And we're gonna have the common networks again. I'm gonna have 192.168.1.0/24. Then I'm gonna have 192.168.2.0/24 and 192.168.3.0/24. And after configuring the basic IP settings, what you can do is advertise your networks. But before that, it's going to be much easier than the static route that you did. So I can say no here, enable, configure terminal, then interface FA0/0, no shutdown, IP address 192.168.1.1 along with the subnet mask, and then you can say IP DHCP pool A network 192.168.1.0 along with the subnet mask and default 192.168.1.1. Sounds good. Then you can take an exit and then configure the next interface, which is SE2/0, and say no shutdown and IP address 192.168.3.1 along with the subnet mask, and take an exit from there. You see, that's how you configure the two of the interfaces that you have, which is for FA0/0 and which is for SE2/0. So after that, you go ahead and go to the PCs and configure the IP addresses on them and requesting IP, and there you go. Then I'll go to the next PC and configure the IP address there as well. There you go. And then I can go on over here, CLI, no enable conf interface FA0/0, no shutdown IP address 192.168.3.2.1, and then IP DHCP pool B network 192.168.2.1 sorry, along with the subnet mask and default 192.168.2.1, and take an exit. Interface SE2/0 again, no shutdown, and IP address 192.168.3.2 along with the subnet mask, and take an exit. You see that? That's the normal IP configuration that we have did, and your entire network is up and running. Correct? I can check the routing there as well. Yeah. So I can say over here, do show IP interface brief. There you go. FA0/0 is configured with 1.1, 2/0 is configured with 3.1. And then you can see here, do show IP interface brief and 2.1 and 3.2 there. Sounds good. So when I take an exit there, then you can actually also check the routing table, that my routing table doesn't really contain anything from 1.0. So in the static routing scenario, we kind of added the static route over there, right? But in the dynamic routing, we are not going to add any indirectly connected network into our router. So how do you advertise your route? Your route actually is advertised in a way that you open up a router and you can give this particular router a hostname R1. You can give the other router the hostname as R2 by going into conf hostname R2. Yeah. And then you create a routing rip or RIP instance by saying router rip version 2 and then network 192.168.1.0. You need to advertise your first directly connected network. Then you say network space 192.168.3.0. You advertise your second directly connected network. Make sense? And then after that, you go on to the other router. You can check the routing table that 2 and 3 are the directly connected networks. So you create router rip instance by saying router rip. Then you select version number 2 there. And then you say network space 192.168.2.0 and network space 192.168.3.0. You get that? And after you advertise both of these networks, then the router will send an advertisement of all the routes that this particular router knows about and all the routes that the other network knows about. Okay? into one another. Make sense? Then if I go on to the first router and if I check show or do show IP route, then you can see that there is a new new update there in router ref that says 192.168.2.0, which is highlighted with R, and R stands for RIP. Okay, so this particular route has been learned via 192.168.3.2. Okay, and it has been learned from, like, it has been 9 seconds since this particular router learned about that route, and the advertisement was received on SE2/0. Similarly, if you go on to the other router and check the same by saying do show IP route, you will also see a router. There you go. You have a route that has been installed with the help of RIP, routing information protocol there. Okay, and that particular route has been received uh, via SE2 via 192.168.3.1. And now if I go back to the topology and if I try to send traffic from here to here, okay, the PC doesn't have any ports functional. I'm gonna go and configure the IP addresses on these devices. DHCP, and it's working. And then DHCP, and it's working fine. There you go. And then if I try to send traffic now, first packets probably would be failed because of ARP resolution, yeah. And then second successful. You see that? Then I can send traffic. First failed, second successful. There you go. And then I can send traffic over here and every communication will be successful there. Make sense? So this is how routing information protocol actually works there. I hope you understand that. Yeah. So go ahead, try this small configuration. The only command that we have used is just a minute. The only command that we have used is network, or when you go into router rep, yeah, router rep version 2, 192.168.1.0 and 192.168.3.0. Rest, you are familiar with the remaining configuration. So go ahead, try this particular lab up and see if it works for you. And then we'll move on with the next information that you need to be aware about RIP. Okay, as most of you are done, I believe, configuring the lab, we will move on and understand how exactly the RIP works there. Correct? Right, I hope you can see my screen now. Perfect. So, as you can see, this is basically the topology that we have, which means if I specify how we are working over here, then you can get a view of it in a way that you have your directly connected network as 1.0 and 3.0, which are known to this particular router. And then you can also get to know that 2.0 and 3.0 are known to this router, which means the router actually, or both the routers actually have a common network, which is 192.168.3.0. You get that? Now, when I say the characteristics of packet tracer, which, so we will discuss some of the characteristics as it's an open standard protocol. Then the second characteristics that we actually discuss is classful nature, correct? Which means it can advertise the routes that are not classful, that are not of classful network. And then the third characteristics is updates are sent on 224.0.0.9. You get that? So when I showed you that the static route, or that whatever you have over here, whenever, not the static route but the route that is learned by the router, keeps getting updated every 30 seconds. Okay, which means that it uses periodic updates. RIP, routing information protocol, uses periodic update for 30 seconds. Every 30 seconds, your router is going to send an advertisement on on a destination address called 224.0.0.9. It is not going to send a unicast message to R2. It is going to send a multicast message, and that particular multicast message will target to the other host as well. Which means that if you have different host, if you have like connected with R3 as well, and then connected with R4 as well, so this R2, R3 and R4, all these routers needs to receive the routing update from R1. So that's why R1 is not going to send individual packet to this router, then to this router, and then to this router. It is not going to work like that. The router or the rep will just initiate a single message onto this destination, which is 224.0.0.9. And any router who has a routing information protocol configured on it is going to receive that particular routing update every 30 seconds. And by the way, this is one of the biggest drawback as well of routing information protocol, that it sends periodic updates every 30 seconds, and that's why it consumes unnecessary bandwidth. Okay, it consumes very unnecessary bandwidth there that it should not consume, because even if there is no updates, or even if there is no changes inside your network, your routing information protocol is going to exchange the I would say route every 30 seconds, no matter what no matter how or what the network has been performing to. You understand that what I'm saying? So that's one of the characteristics there. Then, if we talk about the fourth characteristic, you can see that it uses metric as hop count. Now, understand this term very well. Can you tell me that if I look into my R1, or if I look into my router 1, then my router 1 actually has two different routes advertised. Okay, on router 1 we have advertised 1.0, and on router 1 we have advertised 3.0. So when R1 is initiating a routing update on 224.0.0.9, how many routes is R1 advertising? What do you say? Can I say R1 is advertising? Yeah, exactly. R1 is advertising two routes. But if I go into one of the router that is connected in my RIP, or if I go into R2, how many routes do you see over there? If I go over here and if I show you enable and conf t and show IP route, oh sorry, do show IP route. How many routes do you see? There's just one route that has been learned. I'm talking about this route. This this is a route that has been learned by rep, right? But our R1 advertised two routes, which was 1.0 and 3.0. Why don't you see 3.0 as a rep route? You of course have a route that says 192.168.3.0, but that particular route is not there as a routing information protocol route or as a rep route. And why is that? Because it is connected directly. And what difference does that make? I mean, based on what terms the router actually identifies that it should not install the route that is learned by rep into the routing table, and it should install the route that is directly connected to the router into the routing table. On what grounds does the router makes this particular choice? Exactly. So as RJ is saying in the chat that it is depending or it is making that particular choice with the help of the administrative distance or AD value that you have. Okay, because when we look at the topology, then you would basically see that the administrative distance or a static route has an administrative distance of 1. Directly connected route has an administrative distance of 0. And a route that is learned by RIP has an administrative distance of 120. So when the R2 receives a route, one via static and the other one via RIP. However, the route is just like 3.0 and 3.0. Okay, even though after that the route, I'm when I say static, I'm indirect. Okay, directly connected network. So when I say that this particular router knows these route or knows this network with the help of directly connected network, then which has an AD of 0. So this particular lower value wins over the higher value of RIP. So whenever the R2 is receiving an update for 3.0, it checks the AD value of that and the router prefers the route that is directly connected. Okay, and it doesn't prefer the route that is not directly connected or that that is connected but the update about that is being given to it with the help of a routing update and the AD of which is much higher than the route that is available there. That's why it's gonna make a choice of choosing the you can say directly connected route over the static route. Sounds good? That's one of the term over there. The second factor when choosing the best route to be installed into the routing table is the router is going to make that particular choice with the help of a metric value. And in RIP, the metric is basically used as hop count. Okay, so it uses hop count as its metric, which means if I have a parallel connection like this, I have an R1, I have an R2, I have an R3, and I have an R4. And I want to reach out to a network over here, 40.0.0/24 from here. So R1 will kind of decide that how many hops do I really need to cross in order to reach out to the destination network, which is 40.0.0.0. And in that scenario, the network is actually shown to you, or the network is actually visible with the help of checking that the R1 is actually reachable to R2, R3, and R4 by crossing like 3 hops. So it can reach out to 40.0.0.0 via R2, R3, and R4. So then the R1 will make an entry that 40.0.0.0 is known with the help of 120 AD and 3 hops away. You see that? And this particular information is called as metric. The value of that particular metric is called as hop count. And based on this hop count, since routing information protocol or since every router that is using RIP makes its decision based on the distance that the network is situated at, it considers that particular value in order to calculate the best route possible. That's why it is called as distance vector protocol. It makes the decision based on the distance that the destination device is or that the destination network is situated at. Do you understand what I'm trying to say? Yeah, perfect. And you can verify that particular thing into the routing table as well. That you will see this particular bracket value. I will show that to you as well. If you go over here, yeah, if you can check that R1 has learned this particular route and this information specifies in the bracket that 120/1 is actually 1 over there is basically the metric of the destination device 2.0. Okay, that's how it decides that it is the best route possible. Yeah, it's 1 hop away. Okay, that's how it knows it. Then another important characteristics of RIP which we need to discuss about is if I talk about the fifth characteristics, then load balancing is supported, which means load balancing of four equal costs is supported. Your RIP or your routing information protocol supports load balancing of four equal costs. Now, what does this mean? Suppose you have an R1 router and that R1 is connected to R2, R3, R4, and then R5. And this R2, R3, and R4 are connected to this R6, which is just one hop away. But this R5 is connected to R6 by going through R7 like this. So can I say that R1 has a route, let's say that route is 60000. Okay. So R1 will make an entry of a route that is learned with the help of RIP, which is 60000, and the AD will be 120 and the metric will be 2. It is 2 hops away. Right? How many routes with the same details will R1 have? Can I say R1 can have 3 routes of such detail? Correct? And then, you don't get it? I am saying that you have an R1, right? And in that particular R1, you have R2, R3, and R4 connected over there. So, R2, R3, and R4 are giving or they are advertising the information about R6's 60000 to R1. And both of those, like all of those neighbors, which is R2, R3, and R4, they will actually have the information that 60.0.0.0 is connected to them, or they are giving the information about that particular route that they are connected via 2 hops away with R1, right? So R1 is going to add that particular route into the routing table. But the decision over here needs to be made that when I said that your load balancing of four equal cost can actually be made, it means that you have three paths that actually makes this particular network reached out. But this last route uses hop count of 3. That's why this is not same as the metric of the previous route that has been learned. Although all the routes are there and they all make you reach out to the destination network, but only the shortest distance route will be considered over there to be added into the routing table. And what is that route? The route that actually makes you reach out to R6, okay, far like in a shortest with the shortest number of hops, which is R2, R3, and R4. So you have a tiebreaker, or you have three such networks that actually makes you reach out to the destination with the same number of hops needs to be crossed. But the last route needs to be like added into the routing table with the hop count of 3, not with the hop count of 2. That's why it doesn't become eligible. And only R2 and R3 and R4 will actually be able to install the route into the R1's routing table. Okay, because in that case they will do load balancing of four equal cost path. Okay, whenever you have multiple routes that actually has the metric value same for a same destination, then you call them as equal path cost. And then the traffic between equal path cost is shared. So you can have such four such equal cost routes installed into your routing table for one network. Do you understand what I'm trying to say? No, load balancing is not a tiebreaker. Load balancing is that one by one they will share all the packets. So your traffic will go with the first link as well, the second link as well, and the third link as well. Okay, but your traffic will not go via fourth link. No, the traffic will go with 120/2. Okay, why will it go via 120/3? It will not go via 120/3. Make sense? Perfect. So that's something that needs to be understood by you guys. Then after that, the next characteristics that we have. Let me just get done with this particular thing. So the next characteristics is maximum hop that is allowed is 15. In routing information protocol, you cannot connect more than 16 routers together and send your traffic. You understand that? Which means if you have your R1 here, then you have your R2 here, then you have your R3, R4, like that, you can only have R15 in the serial connection. Okay, if you have your R16 and if you have your R17, then the network that will be advertised by R1 will not make it out to the 16 and 17 and any router after that. Your traffic can only go till the metric value that it reaches to 15. Do you understand that? That's why it has a characteristics that maximum hop that is allowed is 15 only. Okay, yeah. And as I've told you that they exchange the routing table every 30 seconds. So these are certain characteristics that RIP actually uses. I hope all of that characteristic is clear to you. No, you are not going to configure a network with the metric, right? With the hop counts. You basically receive advertisements there, and you receive advertisements with the metric value given inside of that advertisement. So if your router receives an advertisement that actually has metric 16 or that actually is coming from a router which is situated 16 hops away, then your router will not accept that particular traffic. Okay, it will drop that particular route, assuming that this particular route is not supported and I cannot reach out to a router or I cannot send traffic to a router which is situated 16 hops away from me. So that particular route will not be installed into your routing table. Yep. These are certain characteristics of RIP and how it actually works. Yeah, let me clear the screen. And that was basically something that we had to discuss about RIP, you can say. Okay. Then there are certain things that we also need to discuss, which are RIP timers and all. But we will talk about those timers once we move on to the next protocol, and compare them with the pre-existing ones. Cool. The next protocol that we're gonna have is EIGRP. All right. As we discussed about how uh, RIP works, in comparison to that, we're going to see now how actually EIGRP works. So let me share my screen with you all again. Oh, it's already shared. Now, in this session, we're going to move ahead. So, welcome back to another session of our CCNA training, and I am going to start with the session, or start this session with discussing EIGRP. Okay, as you can see that in the previous section we discussed about RIP and how RIP actually works. We're going to discuss some of the fundamentals of EIGRP, and then we'll move on and configure EIGRP for the same. So this was our topology that we actually used for routing information protocol, and we probably will be using the same topology here, but we'll just compare this particular topology with the other like with the contrast concepts that are available in EIGRP. But in order to be able to get to know about how EIGRP actually works, first let's get to know about the fundamentals that you have. So if we talk about EIGRP fundamentals, then EIGRP, as most of you might know, it stands for Enhanced Interior Gateway Routing Protocol. Correct? Enhanced Interior Gateway Routing Protocol. And it is called as Advanced Distance Vector Protocol. Okay, Advanced Distance Vector Protocol. So I'll talk about why this is called as Advanced Distance Vector Protocol, because we have seen how RIP actually works, and RIP has worked something which is called as Distance Vector Protocol. And why RIP is called as Distance Vector Protocol? Because it makes the forwarding decision based on how far the destination is situated, which means it takes the forwarding decision based on the number of hops that the destination network is away. If you have a scenario like you have R1, and then you have R2, and then you have R3, and then you also have a scenario where you are directly connected with R1 and R2, and then this R3 has a destination network of 30.0.0. Then even though that your R1 has a way to forward that traffic via this, or your network can actually forward the traffic via the other way as well. So based on that particular scenario, your router is going to, you can say, take some decision that how to forward that particular traffic there. Makes sense? And the decision is going to be made not based on how, like, what the link is connected, what it's connected with the link of, or how good that particular link is, but it is purely going to be based on something you can say. Yeah. So if you have your R1 connected via two routes to R3, then it's gonna make this decision from either here, or it can forward the traffic from here as well. Okay. And as your router one will take the decision based on the number of hops away. So if it takes the first route, which is actually connected from R1 to R2 to R3, then it needs to cross two hops, right? But if it considers the second route, which directly connects R1 with R3, okay, then it just needs to cross one hop. And that's why this particular route becomes the winner. Okay, and then the R1 will basically forward the traffic based on this particular route over here. Do you understand what I'm trying to say? This is how distance vector protocol actually works. But over here, as I told you, even if the link that is being connected between R1 and R2 and R3 is, let's consider that the link is made up of 1 Gbps. This is a 1 GB link and this is a 1 GB link, and the other link is of 100 MB. So even though the number of hops for the second link, okay, it's just one hop that R1 needs to cross in order to reach out to the destination. But if we look at the other route, which is the first route, then the link is faster. even though it needs to cross two hops. So even though the bandwidth is faster and in real time, your traffic will actually reach out to R3 faster if you send it via R2. If you have configured routing information protocol, then your traffic will still go via R1 to R3, which means by taking the second out, because RIP works based on not based on how fast the link is, but based on the information that how far the destination is. Okay, that's why the number of hops is an important criteria, or it's the only criteria that is considered while choosing out the best path in routing information protocol. Do you guys understand that? Perfect. So when I tell you about the same thing there, so yeah, when I'm actually talking about that EIGRP is an advanced distance vector routing protocol, what I mean that it doesn't only consider the fact that how far your destination is, but it also considers the other parameters of the network as well, be it bandwidth, be it load, be it something else, and it's gonna take the decisions based on that particular information. So that's one of the second criteria that EIGRP considers. The next factor that the EIGRP will consider over here is that if we talk about the next factor, then EIGRP, let me change the color of that. Yeah. So the third parameter over there is very common that it's classless routing protocol. Okay, just like RIP. So it supports classless behavior of it now. Yeah, as I was telling you, that it supports the classless routing protocol, or it is classless behavior of it. Makes sense? And then after that, you can say, which means that you can send traffic or you can advertise your network of /24 or be it /27, be it /28 or something else as well. Okay. Then if we talk about the next one, then you can say that it is an enhanced version of the predecessor. So you can say it includes all features of uh, IGRP. IGRP stands for Interior Gateway Routing Protocol, which was a previous version of EIGRP. And EIGRP is just like you have RIP version 1 and just like you have RIP version 2. Okay, there was, first of all, in comparison to RIP 1, you had IGRP, which is Interior Gateway Routing Protocol. And then you have EIGRP in comparison to RIP version 2, which is an upgraded version of IGRP. Okay, so this is how the transition actually works. So EIGRP contains all the features of IGRP, and then it has some additional features of it as well. So you can say that it includes all the features of IGRP, and after that, there is no, you can say, caring that is done, because the maximum hop or the max hop supported or the max hop count in EIGRP is 255, which means you can have R1, you can have R2, you can have R3, and just like that, you can have 255 routers that can actually be serially connected, and your traffic will still reach out to the 255th router there. However, if you consider that the default value for the maximum hop is only set to 100, okay? So by default, your packet cannot or your traffic cannot go beyond 100 routers, but you can increase that particular value to 255. Make sense? So just like that, you don't need to actually worry about the number of hops that you have, because you're not serially going to be connected with that many routers in the production environment. There can be scenarios of the very big environment there, but yeah, then there are other protocols that are also considered over there for creating the connectivity. Okay, this is one of the parameters that you have. Then after that, what you need to consider is the AD value of EIGRP is 90. Okay, so just like RIP has an AD value of 120, EIGRP actually has two values. Okay, you have 90 and you have 170. So this 90 is for internal networks and this 170 is for external networks. Okay, which means that basically whenever you exchange a route between one organization, you call those particular routes as internal routes. Okay, the subnet might be different, but if you want to, like you can say, import the routes of some other organization or some other, you can say, building inside your primary building or so, then those routes will be considered as external routes and EIGRP treats them differently. EIGRP has a different administrative distance value for them. Okay, but that's none of our concern as of now because we're still about to understand how EIGRP works in that concern. So you can just understand this particular thing, or you can just note this particular down, or note this thing down, that EIGRP has two values, two AD values, or administrative distance values. Okay, one is 90 and the other one is 170. And yeah, the Amar, yeah, as I told you that the RIP has an AD value of 120. Okay, RIP uses an AD value of 120 there. Then after that, you can say EIGRP is considered as 100% loop-free protocol. This is just one of the characteristics that for now you can just write it down, that it's 100% loop-free protocol and it doesn't create any loops. Okay, because of the behavior of how it actually behaves. Then if I talk about the next parameter, then you can say that the updates, routing updates, are sent on 224.0.0.10. Okay, so routing updates are sent on 224.0.0.10. RIP used to send the routing updates on 224.0.0.9, but over here there is one such a big difference between RIP and the EIGRP over here, that if you consider RIP uses something called periodic updates. Makes sense? And EIGRP uses something called triggered updates. What does this mean? So, for example, if you have a network like this, and then there are multiple networks. This is one switch, this is another switch. You have PCs communicated over here or connected over here. This is 1.0, 2.0. And then you have another network over here, which is 3.0, and it is connected with 4.0. Do you understand this topology? So for now, you can consider this in a way that, let's say there is communication that is happening from here to here, from here to here. You get that? So your EIGRP or your RIP, your routing information protocol, is going to exchange traffic between R1 and R2, which will be called as routing updates every 30 seconds. You understand that? Now let's assume that there is this new network that actually got attached with R2. Okay, and this particular network is called as 5.0. So RIP instantly will kind of advertise that particular new route, and it will create instantly a new route, like routing update. And then again, it will carry further that particular advertisement every 30 seconds. So this type of scenario, we understand it with something called periodic updates. But this is not how EIGRP actually works. Okay, EIGRP works on triggered updates, which means if you already have your network converged, which means this is your network. And at the beginning of when this network was actually being built, for the first time, the routers will exchange the routing updates by creating something called neighborship, EIGRP neighborship. Okay. And once the entire routing table is exchanged, or once the routes that are advertised are exchanged between the neighbors, then there won't be any update that will be sent. Okay. And if there is any new network that comes up that we had, like let's say 5.0, then and then only R2 will initiate a new, you can say, packet that says, hey there, R1, I have an update for you. There has recently been a new network that has been added into my topology, and here's the detail of that particular network. So then R2 will give the details of 5.0 to R1. Do you understand that? Even you need to understand over here that R2 is only giving the change, not the entire update again and again, like what RIP does. If this particular change would have been made into RIP topology or routing information protocol topology, then the RIP router would have been given the entire routing table again to the R1, that hey there, this is my entire you can say routing table again, and make changes into your routing table accordingly, because there is some change in my network as well. But EIGRP doesn't exchange any routing update until unless there is any change in the network. And whenever there is any change in the network, the router is only going to advertise that specific change and not the entire routing table. Do you understand the scenario? Yeah. So that is what the behavior of EIGRP is. It means that routing updates are sent on 224.0.0.10. Okay, again, I'm telling you that the update that R2 will give, which is going to be a triggered update upon a change in the topology, will again not be any unicast message. It will be a multicast message that will be sent on 224.0.0.10. Okay. And you can check the current routing table manually over there to see if there is any change in the network. Okay, you can do, yeah, all those modifications can actually be done. Yeah. And yeah, that's exactly what triggered update means. Okay, and EIGRP works according to the triggered updates and not the periodic updates every 30 seconds like that. And this kind of behavior of EIGRP saves a lot of unnecessary bandwidth utilization that gets done by RIP if you have RIP in your topology. Makes sense? So yeah, that's one of the attributes there. Let me clear this window here. Then the next characteristic of EIGRP that you can see over here is hello packets are sent every 5 seconds. You see that? Hello packets are sent every 5 seconds. Now, what does this particular thing mean? Now, if you consider a topology that you have in RIP, I'm going to again create the same topology that you have R1 here and that you have R2 here. And then in R1, you have a network like this, and then you have R2 and you have a network like this. You have 1.0, 2.0, and 3.0. So in such scenario, how are you going to keep your network updated? Let's assume that the network that you're talking about is no longer available, which means there is any layer 1 or layer 2 or layer 3 issue, and due to that 1.0 network is no longer available. So how would the other router in RIP will get to know about that? So that's why in RIP there is something called RIP timers. Okay, and when you talk about these RIP timers, then you will actually get to know that the first type of timer that you have is update timer. Update timer, which is of 30 seconds for the periodic updates, right? So whenever you like, your router will send you a routing update every 30 seconds, irrespective of whether there is any change or not in the network. We already have discussed about this. The second type of timer that you have here is called as invalid timer. Okay, and this invalid timer by default is set to something called 180 seconds, 6 times of update time, which means if this network goes down, then until unless 180 seconds, R2 will keep on waiting for that particular update, which means before R2 removing that particular route from its routing table, it will wait for 180 seconds for that route to come back again. Okay, because as soon as the route goes down, then R1 will stop advertising that particular route from the next update. Do you understand that? From next update, R1 will not advertise that route because R1 will get to know that, hey, there, my 1.0 network is down. I cannot advertise that particular route anymore. But still, R2 will maintain the previous information about 1.0 till 180 seconds. Makes sense? In a hope that in like within 180 seconds, the network admin will try to fix something and the network will come back up again. So in order to save the extra processing, R2 kind of maintains that particular route into the routing table until unless invalid timer crosses. Then there is a third timer called flush timer. And this flush timer is set till 240 seconds, which means that after 240 seconds, the router removes that particular route from the routing table. Make sense? This is exactly how the communication actually works. And in CCNP, you will learn about all the disadvantages of this behavior of RIP. Okay, because due to such behavior that it maintains the route for certain amount of time, even after the route is no longer available. Okay, due to such behavior, there can be loops created and there can be some other scenarios that can actually harm the network. And yeah, these timers are not editable. These are the fixed timers that you have. Okay. So far we are like concerned about RIP. The RIP's timers cannot be modified over here. Make sense? So update timer basically is the time between the consecutive updates that R1 actually sends. Then invalid timer that we discussed is basically a time a router waits to hear an update from the router or from the other router that the route was actually learned from. And you can say the route is marked unreachable if there is no update during this time interval. And the third timer, as I told you, is a flush timer, which actually you can say is a time before the invalid route is removed from the routing table. And then there is a fourth route as well, which is called as a hold down timer, which is again called as 180 seconds. Okay, so this invalid time and hold time is actually same. And you can say that this particular timer stabilizes the routing information and it helps to prevent the routing loops during the periods when the topology is actually changing to the new route or so. Okay, so the invalid time and hold time are kind of same. You can consider that. But yeah, these timers are basically there to help stabilize the network when the router or when the topology actually is struggling for fetching out the new way that it can reach out to the destination network also if some route goes down also. It is also possible that this route is not available and then the R2 is actually connected with some other route with R1, right? So there can be multiple scenarios that can be created in order to understand how each of these terms can be created, but you will learn about that in CCNP. For now, you can just consider that these are the timers of RIP. Now, EIGRP doesn't work with such timers here. Okay, you have multiple of these timers, but if we talk about EIGRP, as I was telling you, over here that yeah, flush timer. Yeah, flush timer means that the network will be removed from the routing table, correct? It's about flushing the route from the network, not about flushing the entire network. It's possible that your router is exchanging multiple routes and one of that route is no longer available. So it will remove that particular route, that specific route. Not all the routes, but the specific route which is not being sent by the router anymore in the routing update. And it will remove that after the flush, like during the flush timer. Okay. So as I was telling you that EIGRP exchanges hello packets. It's flushing is basically flushing the specific route, not the entire route. Yeah. So EIGRP uses hello packets in order to exchange traffic every 5 seconds. It doesn't send the routing update every 5 seconds. It sends hello packets every 5 seconds. Make sense? We'll talk about that in a bit, that how this hello packets and all works over here. But for now, you can just have an understanding that EIGRP uses hello packets in order to stay connected with the neighbors that it has or with the routers that it's exchanging the routing table or so. Make sense? So, and then the last characteristic that you need to be aware about is it uses a protocol called dual. Dual stands for diffusing update algorithm. Okay, EIGRP uses dual algorithm or diffusing update algorithm in order to calculate the best route that is there. Sounds good. And we'll talk about how this diffusing update algorithm works. And the last characteristic that you have is it supports both equal and unequal cost load balancing. Unequal cost load balancing. So it supports both equal and unequal cost load balancing. That's exactly how it actually works. Sounds good. So these are certain characteristics that you have about EIGRP that you actually need to understand. Okay, and I hope that makes sense to you. Okay, however, some of them like how dual works and how equal cost and unequal cost load balancing works. We're going to talk about that in just like now 2 to 3 minutes that we're going to talk. But let me know if you understand all of these characteristics like as part of the basic thing. Are we good here? Perfect. Just give me a minute and then we'll go ahead with the next one. So as we discussed about the fundamentals of EIGRP, it's actually time to discuss how this thing works here. So the process can be identified with something called EIGRP neighborship. Okay, and you can consider it as EIGRP, or you can consider EIGRP neighborship in a way that it's a two-step, or you can say multiple-step process in order to create EIGRP adjacency. So you can have your R1 there, and then you can have your R2 here. And let's say both of these routers are actually initiating to create EIGRP neighborship between them. And you can understand it in a way that the R1 and R2 are actually having a network called 12.0.0.24. Dot 1 is here and dot 2 is here. Okay, so whenever this R1 and R2 will actually try or configure the EIGRP and advertise the network, then it's not like that instantly they will exchange the routing information. It doesn't work like that. Okay, whenever you have two routers that are creating an EIGRP neighborship, then they actually go through a series of process in order to become EIGRP neighbors. Make sense? So when we talk about it, it actually starts after configuring EIGRP onto the router. The very first procedure that both the routers will start sending hello messages on 224.0.0.10. They will send multicast hello messages on this particular address, and any router that actually has configured EIGRP will receive that particular hello message. So R1 will also send that, and R2 will also send the hello message on the same address 224.0.0.10. You get that? Then they actually need to become neighbors, because inside of this hello message, yeah, what's gonna happen over here? That let's assume that I go into R1 and then I configure my EIGRP into R1 and advertise my network. Then I go into R2 and I also start configuring EIGRP, and then my EIGRP is configured on. As soon as I configured EIGRP on my router will start sending hello messages on a multicast address that, hey there, is there anyone who has configured EIGRP? I would like to become neighbor with you. Hey there, is there anyone who would like to exchange routing or routing information with me? I'm running EIGRP, like that. It will contain some of the other information, and the hello message will be dispersed onto this destination address called 224.0.0.10. And the hello message contains three neighborship parameters. So you can consider that there are neighborship parameters. The first neighborship parameter is that both the routers who are actually exchanging the hello messages or receiving the hello messages, or who are looking forward to become neighbor, needs to be in same subnet. Okay, they need to be in same subnet. Like you have 12.0.0.0 configured, right? So R1 and R2 are into same subnet via that particular link. You get that? Then the next parameter there is they needs to be into same autonomous system number, same ASN value. So how it works in RIP, if you have R1 and then if you have R2, then you simply go on R1 and you say router RIP version 2 and then network this, network that. Correct? But in EIGRP, it doesn't work like that. In EIGRP, whenever you have multiple routers, then those routers will only be able to exchange routes if they are into the same autonomous system number. Which means if I go on R1 and I say router EIGRP 10, okay, then this 10 is called as AS number, autonomous system number. And if I go on R2 and say router EIGRP 20, then I'm configuring a different AS number on R2, and these routers will not be able to exchange the routes. Do you understand what I'm trying to say here? Which means that for you to be able to exchange the route, your both the routers actually needs to, you can say, exchange the route, or both the routers actually needs to exchange the route uh, with having same autonomous system numbers configured on them. You understand that? So your routers are only going to become EIGRP neighbors if both of them are having same autonomous system number configured there. Okay, that's one of the condition there. And then after that, when you have this particular scenario there, the third parameter that is available there is, and yeah, as we were discussing about EIGRP neighbors, right? Or EIGRP neighborship. And I was telling you that when you have your R1 and then you have your R2 configured there, and both of them are in a same subnet. Okay, you can have .1 configured here, .2 configured over here. And I was telling you that your R1 will send the hello message on 224.0.0.10, and you will get a hello message from the reply as well. as 224.0.0.10 as well, correct? But in order to become neighbors, there are some neighborship parameters. And the first neighborship parameter is that they should be in same subnet. The second parameter, as I told you, that they should be in same autonomous system number. And the third parameter is they should have same k values. Okay, now k values is something that we are going to discuss about later. But by default, EIGRP has multiple k values configured here. Okay, your EIGRP has almost 5k values that actually helps the router in deciding what is the best route. It is part of the diffusing update algorithm that it uses in order to calculate the best route. But yeah, you can consider it like that. That EIGRP uses all these three parameters in order to decide whether it can establish EIGRP neighborship with the router or not. And once all of these routers or all of the neighborship parameters are matched, then and then only they both the routers will actually become neighbors. Okay, and then EIGRP also maintains something called EIGRP tables, and inside of that, the first table is called as neighbor table, and the information about your neighbor will be stored inside the neighbor table upon exchanging the information with the help of hello packets. Do you understand this? Perfect. Then after exchanging the EIGRP information here, what's going to happen is your router then will process in exchanging the routing table. After becoming neighbors, then your R1 will say that here is my routing table. Do you understand that? And then R2 will acknowledge to that particular exchange that, hey there, I have received your routing table. And then after that, it will say, here is my routing table. Makes sense? And then R1 will acknowledge to that particular exchange that I have received your routing table as well. And then there is a second table into EIGRP table, which is called as topology table. And the information about this routing table or all the routes that will be received will from the neighbor will be stored over here into the topology table. Makes sense? And then the best route will be installed into the routing table, which is the third table. And once the best route is installed from the available routes into the routing table, then the network will become on a stage called converged. You understand that? So this is actually how it works. Now, here's something that you need to understand, that what is this transition between topology table and routing table? So, for example, let's consider a scenario over here. I'll give you that scenario that you have something, you can say R1. And with this R1, there are multiple routers that this EIGRP is neighbor with. So you have this R2, you have this R3, and you have this R4. And this R2, R3, and R4 is also connected to another router called R5. Do you understand that? Now R1 has a loopback address called 10.0.0.0, and R5 has another loopback address called 50.0.0.0. And this is the source, and that's the destination of how your traffic needs to actually communicate. Now, can you believe, or can you, when I say that R1 is actually neighbor with R2, with R3 and with R4. And in order to get to know that how to reach out to this destination network of 50, R1 is going to inquire to R2 and R3 and R4. Do you trust that information? That R1 is going to ask to its EIGRP neighbor that, hey there neighbors, do you know any information about how to reach out to 50.0.0.0? And it is possible that R2 has multiple routes that how it can reach out to 50.0. For example, R2 knows about around 3 routes that how to reach out to 50. R3 knows about around 2 routes that how to reach out to 50. And R4 knows about around 5 routes that how to reach out to 50.0.0.0. And all this information, which means that combining all together, the neighbors knows somewhat around 10 routes that how to reach out to the network. Now what's going to happen here, that the R2 will give only the best route out of the available 3 routes to R1. Then R3 will also give its best route to R1 and R4 will also give the best route available to it in order to reach out to 50.0.0.0 to R1, which means R1 is going to receive 3 of the best routes that its neighbor knows about for reaching out to the 50.0.0.0. And all these 3 routes that it will receive from the EIGRP neighbors will be stored into something called topology table. Do you understand this? And as I told you that your topology table is going to have almost 3 routes now. And the best route amongst these 3 routes, only one best route is going to be inserted into the third table called routing table, which means that your topology table can have multiple routes, but only the best route will be inserted into the routing table. And selecting this best route is basically the process of diffusing update algorithm. Okay, dual algorithm does the task of this. Again, we're going to talk about what this dual actually does. But yeah, this is how actually EIGRP does the process of bringing the network up. Okay, and this is how EIGRP neighborship is built up. Make sense? Perfect. Now we're going to see in a topological manner that how you can actually create EIGRP neighborship between the router. Okay, so I'm going to create a simple topology and I'll show you how you can create EIGRP topology by configuring the network with the necessary configuration there. Okay, so I'm gonna erase the stuff up from my script, from my screen. There you go. And then I am going to have a couple of routers here, or let's say we're gonna have around 3 routers. And I'll also place 1, 2, and 3 there. And I will place a couple of PCs along with that. And then I'm gonna connect all of these together by connecting it to R1, connecting it to R2, and connecting it to R3. Okay, we probably need another device there. So yeah. And then we're gonna connect these together as well. Okay, that's how we have the thing here. We have 1.0. Oops. Okay, my note is not working, so coordinate with that. So we have 192.168.1.0. We have 192.168.2.0. We have 192.168.3.0. Then we have 192.168.4.0 and 5.0. It's better that I note it down there. But like that, I will just note it down as 192.168.1.0/24, 192.168.2.0/24. And then I have 192.168.3.0/24 and 192.168.4.0/24 and 192.168.5.0/24 as well. You get that? Just like that. So what we are going to do now, we will basically configure this entire network by configuring the IP parameters first and then by configuring the EIGRP. So I'm just going to go on each and every router there. Yeah, I'm just going to go on each and every router there and configure it. I'm going to go on to the first router. I'm going to say no, enable conf hostname R1, hostname R1. Yeah, and then I'm going to say interface FA0/0, no shutdown. IP address 192.168.1.1 along with the subnet mask, and then IP DHCP pool A network 192.168.1.0 along with the subnet mask and default of 192.168.1.1. Then I'm going to take an exit there and I'm going to say interface SE2/0, no shutdown, IP address 192.168. What's the IP that we're going to configure there? Yeah, 4.0 network. So I'm going to configure 4.1 over here. So I say 192.168.4.1 along with the subnet mask there. And that's all. So we're good with the configuration of R1, and I'm going to go on to the PC of R1 and configure IP address for the host that we have. There you go, DHCP. Then I'll close this router and go back to the second PC. Desktop, IP config and DHCP. And there you go, it's working fine. Then I'm going to go on to the R2 and configure three of these networks, 2.0, 4.0 and 5.0. So I click on this, go to CLI and say no, enable configure terminal, interface FA0/0, no shutdown, IP address 192.168.4.1, sorry, 2.1 along with the subnet mask and IP DHCP pool B network 192.168.2.0, 255.255.255.0 and default of 192.168.2.1. Right? Then I'm going to take an exit, say interface SE2/0, no shutdown, IP address 192.168.4.2 along with the subnet mask and then interface SE3/0 and I'm going to configure that with IP address 192.168.5.1 along with the subnet mask. Makes sense? That's how the configuration actually will be done. And then after that, I am going to the PCs and configure the DHCP addresses there. There you go, it's done. Then after that, if I go here and desktop IP configuration, DHCP, and there you go, 2.3 has been configured here. Then the configuration will be done for the last router there. I'll close down the PCs here and go back onto the third router. Enable config T hostname R3 interface FA0/0 no shutdown IP address 192.168.3.1 255.255.255.0 IP DHCP pool C network 192.168.3.0 along with the subnet mask and default router 192.168.3.1 along with no subnet mask needed there. Then going into interface SE2/0 no shutdown and IP address 192.168.3. Sorry, not 3.1. It's gonna be 5.2. And there you go. The configuration is done. Then we will go on to the PCs of the R3 and configure the IP addresses there. There you go, IP done. Then I'm gonna go on to the last desktop, IP config, and DHCP. And there you go. Then I'm gonna close this down, go back to this, and yeah. So right now, if I check the routing tables of our R1, there will only be directly connected networks, right? So if I say do show IP route, we just have 1.0 and 4.0. On R2, yeah, then on R2, if I go and say do show IP route 2, 4, and 5, then after that, if I say do show IP route 3 and 5, 3.0 and 5.0, right? So we just have the directly connected networks over here. So when I do configure this particular network here, then we are going to have the same autonomous system number for 3 of these routers. Okay, the EIGRP autonomous system number that we're gonna have is just 10. So I'll kind of create a design over here by putting up a color, let's say a green color. Say okay, and that's how the scenario will be. Yeah, you get that? So that's our EIGRP domain there, 192.168.1.0, 4.0, 2, 3, and 5. All of these networks are going to be part of our EIGRP autonomous system number 10. And how do you do that? It's pretty similar to RIP that we have did, but the only change over here is going to be router EIGRP 10. So we're gonna go into EIGRP 10 there. Just a minute. Yeah, there you go. I hope my screen is back. So this is the topology that we have, right? R1, R2, and R3. And we are going to create an EIGRP domain here on R1, R2, and R3, which is going to be EIGRP number 10. That's going to be the autonomous system number that we have. So what we're going to do here, we're going to say router EIGRP 10, and then we would say network space 192.168.1.0, and then we're going to say 4.0. So just create EIGRP process and advertise both of your networks. That's how easy it is. Okay, then go on to the next router, which is our R2, and then check your routing table, do show IP route, and then I would say router EIGRP 10, network 192.168.2.0, 4, oh sorry, no, that's a false route that I have advertised. So I'll remove that route by saying no network. And then I will advertise the correct route, which is 192.168.4.0 and 5.0. There you go. You see, instantly there is an update that says new neighbor adjacency is up. And then I will advertise my next network, which is 192.168.5.0. See that? And then we will go on to the next router and advertise these. So I'll say router EIGRP 10 and network 192.168.5.0. There you go. New neighbor adjacency done and 3.0. You understand that? So as of now, our entire network is converged. And if I try to send traffic from here to here, the first packet is going to be failed. And there you go, successful. And then from here to here, first fail, successful. So the communication is working all good from here to here, successful. Make sense? So you can see as soon as we advertise our network, it build up an EIGRP neighborship, and it is done so fast. Yeah, it is correct. Now, as I told you, there are three tables, right? You can check your neighbor information by running do show IP EIGRP neighbor. Okay, when you run this command, you will you will get to know about the EIGRP neighbor that you have. Just a minute. Yeah. So So when you run this particular command that says do show IP EIGRP neighbor, you'll get to know about the neighbor that you have, which is just one neighbor, which means that if you look at the perspective of R1, R1 is not directly communicating with R3. R1 is only communicating with R2 for now. And if you go on R2, which is this router, and if I say do show IP EIGRP neighbor, you see, R2 has two different neighbors. It has 4.1 as well, and it has 5.2 as well, which means R2 is neighbor with this segment as well, and R2 is neighbor with this segment as well. I will delete this part here. So that's how actually it works here. Okay, and the EIGRP number 10 over here represents our autonomous system number. So this EIGRP 10 or 10 can be anything. When I say router EIGRP, and if I give a question mark, you can see that it is autonomous system number, and it can be anything between 1 to 65,535. I have randomly taken 10 there, but you can take 20, 30, 40, whatever you want. Okay, and you can build multiple EIGRP processes with the help of that. So when you have this autonomous system number common between the routers that you want to actually exchange the routing traffic, then and then only it will work. Otherwise, you won't be able to create neighborship between the routers that are having different autonomous system numbers. And then if I go on to the third router and do check by performing a command to show IP EIGRP neighbor, then there you go. You just have one neighbor, which is R2 5.1. And then after that, you can also check the routing table by saying do show IP route, and you will see that there are these EIGRP routes that are advertised or that have been received on this particular router, which are 2.0, 3.0, and 5.0. Make sense? So 90 is the AD value, and this whatever this number is, this is basically the metric that it calculates the number according. Okay, for the best path selection. It's a big number, but we're going to talk about how EIGRP actually calculates the metric. So don't worry about that. Okay, we're going to talk about how this number is coming out. But you can, for now, you can consider that this is combination of bandwidth and delay. Okay, for reaching out to the destination. And then you can also check the topology table by saying do show IP EIGRP topology. And this is the topology table that you have. Okay, and inside the topology table, you have all the routes that are exchanged 1.0, 2.0, and passive means the routes are placed into the routing table. Active means dual is actually calculating something. Okay, or the best route is being calculated, but the process is done so fast, it's very rare that you will ever see active or any other state over there. You'll always see passive and passive and passive. Okay, and you learn about every characteristic that you have here inside the EIGRP in CCNP studies. Okay, so this is how you actually get to know about the all the three routes or all three tables that EIGRP maintains, and then how you can actually make the communication possible by using EIGRP. Sounds good to you? Perfect. So go ahead, try this particular topology configuration and see if it works for you. The commands were pretty simple. I'll show those commands to you. There you go. 1.0, 2.0, 3.0. I actually configured it by just saying these were the commands that I used for the directly connected network of mine. This is my routing table and that's the command that I use. So go ahead, try this particular thing and see if it works for you. All right, guys, I hope you are done with the lab. And then there are just certain things that I want you to know about it or to know about EIGRP. So here's the thing. We are going to talk about how EIGRP calculates the best route. So let me just share my screen with you, the other screen with you. Yeah, I hope you can see my other screen now. And we are going to discuss something about EIGRP metric. So in EIGRP has five different values, which are addressed as K1, K2, K3, K4, and K5. Okay. K1 stands for bandwidth, K2 stands for load, K3 stands for delay, K4 stands for MTU, and K5 stands for reliability. So by default, only K1 and K3 is working, which means bandwidth is set to 1 and delay is set to 1. Rest of the values are set to 0. And if you look at the formula that EIGRP uses in order to calculate the metric or the best route, is it's quite complicated, but yeah, metric in EIGRP is, I'll give you a simple formula that it uses bandwidth plus delay multiplied by 256. Okay, which means that if you have a route like this, R1 to R2 to R3, okay, and to R4, let's say, then from R1 to R2, if the link is of 100 Mbps, and this is also of 100 MB, and this is also of 100 MB, then in that case, the bandwidth is the least bandwidth from source to destination, which means if one of the link, or if let's say this particular link is of 10 Mbps, and then this is your source and that's your destination, then the bandwidth that will be considered is going to be 10 MB and not 100 MB. Do you understand that? So it will be the least bandwidth or the minimum bandwidth from source to destination. Okay, but if you have a common bandwidth, which is like let's say combining all together, if you have 100 MB, then it will be considered 100 MB itself. And then the second formula or the second value that will be considered over there is going to be delay. And delay is the combination of delay from source to destination, from S to D, which means, for example, I would say the delay into the for a fast Ethernet link is for a 100 MB link is, let's say, around 100 milliseconds. There's going to be 100 milliseconds over here, 100 milliseconds over here, and 100 milliseconds over here. So totally, it's going to be 300 milliseconds. So this particular thing will be the combination of delay from source to destination, like a time taken from for a packet to travel from one router to other router, and then it will be just a single 100 or 100 mbps is going to be the bandwidth. So for calculating that, it will be something like 100 plus 300 multiplied by 256, and the output of that will be the metric that you will actually see when you perform a do show IP route. Then you see in a route that you will find 90 as the AD and some value. That particular value is actually the output of this. Do you understand that? However, figuring that out is none of our concern as of now. But yeah, this is how actually AHRP calculates the metric. Then it is not the only thing that EHRP needs to deal with, because EHRP also works in a way in order to figure out what is the best route. For example, if I say dual over here, diffusing update algorithm. So when we try to figure out how dual actually works or diffusing update algorithm works, then there are certain conditions. Let's say you have a scenario like this. You have R1, you have R2, you have R3. I'll draw the same topology, and you have R4. And then you have a destination, which is R5. So over here, consider that the metric from R1 to R2 is 10, from R2 to R5 is again, you can say 10. Then from R1 to R2, it's 15 and 15. And from R2 to R3 is 30 and 50. You understand that? So over here, you need to calculate different values, or EHRP calculates different values here. First of all, you figure out what are the candidates or candidate routes. Because if you consider our scenario, then we have three routes, right? The first route is from R1 to R2 to R5. The second route is from R1 to R3 to R5. And the third route is from R1 to R4 to R5. Okay, these are the three routes that you have. And based on that particular route, you need to calculate two values. You need to calculate something called FD, and you need to calculate something called RD. Now, what is this FD and RD? FD stands for feasible distance, which means combination of total or combination of metric from source to destination. And RD is stands for reported distance, which is the metric from next hop to the destination. For example, if you have R1 to R2 to R3 to R4, and then you have 10, 10, 10. These are the metric. What will be the FD in that case? Can I say 30? Because from source to destination, this will be your FD. And what will be the RD? RD will be from next hop to the destination, which is going to be 20. Do you understand what I'm trying to say here? The difference between FD and RD? Yeah. So you can consider that the FD is going to be the feasible distance. I'll repeat the same thing. As I told you, that there are two terms every route is addressed with. Okay. You have feasible distance and you have reported distance. When I calculate the bandwidth, or when I calculate metric between two routes, let's say R1 and R2, this particular metric will be calculated with the help of bandwidth plus delay. Okay. And then it will be calculated in a way that the best route is possible. So it's possible that R1 to R2, and then to R3, and then to R4. You have these four routes connected serially. And every route, according to the bandwidth calculation, has a metric of 10, 20, and 30, let's say. Okay, this is the scenario. So what will be the FD? The feasible distance from source to destination is going to be the combination of all the metric throughout, which means 10 plus 20 plus 30. It's gonna be 60. Do you understand that? And then RD is going to be the value from next hop to the destination, which is 20 plus 30, that will be 50. Make sense? Yes. So this is how these are the two values that EIGRP calculates in order to figure out the best route. Now, based on our example that we have, the FD for the first route from R1 to R2 to R3, what will be the FD there? Can I say the FD will be 30? Sorry, the FD will be 20, right? 10 plus 10. And the RD will just be 10 there, the next hop route. Then for second router or the second route, the FD will be 15 plus 50, 15, which is going to be 30. Okay. And the RD is going to be 15 itself. And then for the third route, it's going to be 30 plus 50, which is 80. And then the RD is going to be 50 itself. Make sense? This is how FD and RD can be figured out. Now, here's the thing. Based on these values, the router needs to figure out two values. One, it figures out successor, and it figures out another thing which is called feasible successor. Okay, it calculates successor and it calculates feasible successor. What is successor? Successor is basically best route, and feasible successor is next best route. Do you understand that? Successor is the current best route from the topology table, because as I have told you, topology table can maintain multiple routes over there. So when I consider this, it means that successor will become the route which with the lowest FD. The route which has lowest FD becomes successor. In our case, who will become successor? First route, right? So this particular route becomes successor. And this route will then be installed into the routing table. Do you understand that? Okay. The route which has lowest FD will become successor, and that particular route will be installed into the routing table. And then what about the other routes? So in order to other route actually intend to become feasible successor, which means if the first route goes down due to any L2 issue, layer 3 issue, or any link failure or so, when that particular route goes down, EIGRP should know the next best route that needs to be placed into the routing table. Okay, so it doesn't wait for the recalculation. It already knows about the next route who is going to be installed into the routing table. Okay, so for that, it actually needs to know about who is going to be the next best route, and that it addresses it as the feasible successor. Now there is something called a feasibility condition, and feasibility condition means in order to become feasible successor, the RD of candidate, just a minute, the RD of candidate must be lower than the FD of current successor. Understand this very well. Okay. In order for a route to become a feasible successor, the RD or the reported distance of the candidate route must be less than the FD of the current successor. In our case, who is the current successor? This route, right? And who are willing to become feasible successor? Both of these routes. So for the second route to become feasible successor, the RD of that route must be less than the FD of the current successor. And does it satisfy the condition? Is 15 less than 20? Yes, right? So that's why this particular route will become the feasible successor. It's quite complex, but yeah, if you understand it clean and neat, then you will make more sense of it. And what about the third route? Does third route satisfy the condition to check whether the RD is less than the FD of the current successor? If you consider the value is 50 less than 15. No, right? So that's why that's why what's going to happen, then the router will drop this particular route and it will not accept that particular route, or it will not insert that route into the topology table for now, and that route will not become anything. And the route which is this one, the first route will go into the routing table, the second route will stay into topology table. If the first route goes off, if anything happens to that, then the second route, which is the feasible successor, will become the successor then, and it will be placed into the routing table. Do you understand how this works? Perfect. So that is exactly how it actually works. Okay. And I hope you understand how EIGRP actually works. You can check the values of how the values of these can be checked. I would also show that to you. Let me share my other screen with you. There you go. If you look into our topology, then I can show you. Do you see? I'll show you the topology table. There will be link failure over there. That's why there are so many messages. But show IP interface brief. Or not show IP interface brief, show IP route. Oh, do show IP route. There you go. This particular value is called as FD. Okay, feasible distance. And if you check the topology table by running show IP EIGRP topology, then you can see for a specific route. There you go. This is the FD and that's the RD. You see, RD is lesser than the FD. RD will always be low than the FD. Make sense? You see, RD is low than, sorry, FD is greater than RD. So you will see both of these values into the topology table, and the route that actually has the lowest FD is going to be inserted into the routing table. Make sense to you? Do you understand that? If the feasible successor even goes down and then there is no route, then friends, there won't be any route there. You need to do the manual troubleshooting for that if there is no route. Okay. Then the third route will be advertised by the router in that case, and that particular route will become the successor in our case. Okay. Yeah. So that's exactly how EIGRP works. And that is actually all that we had to discuss in this particular class. So today we discussed about how RIP works, and we discussed about how PIGRP works. In tomorrow's class, we'll be discussing about how OSPF works. Okay, and then we'll also see some switching methods as well. Good. So I hope you enjoyed today's class, and that was kind of a complex concept that we discussed today, but I hope I made it clear to you in the simplest way possible. So thank you so much for joining in. I wish you a good day ahead. Till then, take care of yourself. Bye bye. Thank you so much for joining.
If you enjoyed the content of the video, don't forget to like and share the video and subscribe to our channel.
Hey there, welcome back to another session of our CCNA training by Pynetlabs. And in this session, we're going to discuss about OSPF, Open Shortest Pathways. As you already are aware about, in the last session, we discussed about PIGRP. And in this session, we are going to dig deeper into another routing protocol that we will use. So I hope I am audible to you. Perfect. Let me just share my screen with you all so that we can move on. And there you go. I hope you all can see my screen now. All right. So to start with, we have seen now how RIP works, or Routing Information Protocol works, and how EIGRP works, right? So earlier we discussed about some of the methods that we can actually configure routing with, because we have been going through from the similar topology itself, that we saw how R1 and R2 and R3 can actually communicate together if we connect them in a network or so. But the protocols that we have used so far has been about RIP and EIGRP, and I'm talking about dynamic protocols and not static routing protocols. So static routing protocol is somewhat we have explored so far, okay? And then after that, we moved on to the dynamic routing protocol, in which we explored about routing information protocol and EIGRP in the last session. So we're going to move ahead, and we are going to discuss something about OSPF, which actually stands for Open Shortest Path First. Now, almost every one of you might be familiar about what OSPF is and how OSPF actually works, but there are a lot of different factors as well in order to consider whether and how to use OSPF in a specific production environment and so on. So we're going to dig deeper into that itself, that how we can actually use it. So let's go ahead and see how OSPF works, and we'll discuss about some fundamentals of OSPF, and then we're going to see the implementation of how OSPF is actually OSPF works. So if we talk about some of the OSPF fundamentals, then you can say that OSPF again is an open source protocol, or you can say, yeah, open standard protocol, or you can call it as open source protocol, where you can the source code of that OSPF is open for everyone, and people can actually use it for the networking devices that they want to connect their network with. So if you have a device of let's say a Cisco, and if you have a device that is not of Cisco, but you still can make them communicate with each other, and you still can make them exchange the routing tables that they have with the help of OSPF. Make sense? And if we talk about another, you can say, property of that or characteristics of that, then OSPF is a completely linked state routing protocol, which means, unlike EIGRP that considers multiple values or multiple factors in figuring out the best route, in figuring out the best way to reach out to the destination. Like if we talk about EIGRP, then EIGRP works with different K values, right? K1, K2, K3, K4, and K5. However, by default, only K1 and K3 is considered, which are basically bandwidth and which are delay in terms of figuring out what will be the metric. But if you change the K2, K3, K4, and K5 by default from 0 to either 1 or 2 or something else, then you can say factors like MTU, factors like load of that particular bandwidth, and factors like reliability will also be considered in order to figure out what is the best route in order to reach out to the destination. But OSPF doesn't consider all these factors. OSPF is a pure link state protocol where it takes all the decisions based on the bandwidth of that particular link. Okay, that's why it is called as link state routing protocol. And EIGRP is called as advanced distance vector routing protocol because it takes decisions of how to forward that particular traffic with what route and so based on certain values that are available, in which by default only bandwidth and delay is considered. But over here in OSPF, it is pure link state protocol, as I told you, and it uses or OSPF. However, I'd like to tell you that OSPF uses shortest path first algorithm, or you can call it as SPF algorithm. Okay, or you can also call it by the name that is called as Dijkstra algorithm. The official name of that algorithm that OSPF uses is called Dijkstra, but people also refer to the calculation as shortest path first. So we call it either SPF algorithm or Dijkstra algorithm. Okay. Then, unlike other protocols like RIP and EIGRP, which provides you the ability to connect number of hops in your production environment, OSPF has a support of unlimited hop count. You don't need to really worry about how many hops do you actually need to connect together and how many hops you can say your router can actually communicate to. There's nothing that needs to be concerned about over here. Okay, so you can connect unlimited hops. Whether in RIP, you can only connect 15 hops, and in EIGRP, you can only connect around 255 hops. Make sense? But and by default as well, in EIGRP, you only have 100 hops that are connected there. So that's one of the parameters that you need to be concerned about. Then, if we talk about yeah, this can be also said as the most preferred routing protocol in terms of being used because it has been open source since the beginning and it has been open standard since the beginning. Unlike EIGRP, which became open source in 2013. Previous to that, EIGRP was a proprietary protocol which could also only be implemented into Cisco's devices. But now EIGRP can also be implemented into like other vendors' devices as well. But people have already adapted who uses devices that are not made by Juniper or who have a mix of infrastructure. They have been using OSPF for a long time and nobody would look forward to actually change the entire routing protocol just because OSPF went public. Okay, so that's one of the parameter there that OSPF is kind of the largest popular protocol for the IGP for the interior gateway routing. Okay, or as an interior gateway protocol there. Good. Then the next characteristics you can say that is the AD value of OSPF is 110, 110. Make sense? The AD value of OSPF is 110, and unlike EIGRP, there is no internal or external AD. Like EIGRP has multiple ADs, right? It has 90 for internal and 170 for external. But OSPF only has a single AD that is 110. Okay, and the metric. Now you are familiar that how metric is calculated. We have seen it in RIP as well. That the metric is based on the number of hops the destination is away, and in EIGRP the metric is calculated by considering the addition of bandwidth and delay, and the product of 255. Okay, but over here the metric calculation is pretty easy. The metric calculation just uses a formula that says cost is equal to, or metric is equal to, 10 to the power 8 divided by the interface bandwidth. Okay, and 10 to the power 8 is basically nothing but 100 Mbps. So if your link, or if your R1 is connected with a router called R2 and the link is of 100 Mbps, okay, then in that case the cost of that particular thing will be 100 divided by 100, that becomes 1. Makes sense? If you're using a serial line to connect like these two routers together, then the link between that will be 1.54 Mbps. So the formula over there will become 100 MB divided by 1.54, and that actually becomes somewhere around 65. So that's how the calculation would be done. So if you have R1 connected to R2 and then R2 again connected to R3 with a serial link, then the total bandwidth from here to here will be 65 plus 65. That will be somewhere around 130 or something like that, or 128 or something like that. Do you understand what I'm trying to say? That's exactly how metric is calculated in ENGRP. It's not that difficult, but yeah, this is what the formula is. So the 10 to the power 8, we call it as an reference bandwidth, and it is divided by the interface bandwidth. So reference bandwidth is always considered as 100 Mbps, okay, which is 10 to the power 8. And the interface bandwidth can be considered whatever that particular thing would be there. Sounds good? So these are certain parameters that we have in OSPF. Then after that, you can say that it is, of course, like all the features are there. We can consider that it is a complete classless routing protocol. Okay, which means just like RIP, EIGRP, OSPF also supports advertising the routes if they are of like subnetted, if the routes are subnetted like /27, /28 or something like that. Okay, then after that you can say that it supports, just like RIP and EIGRP, it supports VLSM and CIDR because of the nature that it supports uh, classless it supports classless routing as well. So that's why it also has the support of CIDR, which is classless interdomain routing. Then after that, it only supports equal cost load balancing. It only supports equal cost load balancing. What does it mean? You see, we talked about EIGRP and we saw something like that. Like there was a characteristic that said EIGRP supports unequal cost load balancing as well, right? If you remember that. For example, if you have your R1 and if you have your R2 and if you have your R3 and if you have your R4, then there is another router called R5 that actually connects directly to R4. Now, in that case, both the routes will be making you reach out to the destination. And if you have another route, let's say you have R6 and you have R7, and then that R7 connects to R4. You understand that? Now, over here, you have three different paths, right? If I talk to you about that, this is path number 1, then this is path number 2, and this is path number 3. Your path 1 and path 2 might have a similar metric, which means they, let's say that they all reach out to the destination with a metric of 65. And then you have path number 3 that actually reaches out to the destination with the, you can say 80 as its metric. So in that case, which route will be installed in your routing table? Obviously the route that has a lower metric will be winning that, but over there as well there is a tiebreaker, which means there are multiple routes that actually have similar metric, which is path number 1 and path number 2, and that's why this particular route will be inserted over there. However, if you want, in EIGRP you can also make the third route which has a greater you can say AD value there, or a metric there. you can also make that particular metric reach out to the destination or get installed into the routing table. You understand what I'm trying to say? So OSPF only supports load balancing of equal cost, which means that if you want to install multiple routes into your routing table for the same destination, then the metric of that particular route needs to be same. Do you understand what I'm trying to say? All right. Then, after this particular characteristics, you also need to understand that just like EIGRP, OSPF also sends hello messages. We just discussed about how uh, EIGRP actually works in terms of sending creating neighborship, but OSPF also sends hello message, and that particular hello messages goes out to, or you can say the updates and hellos are sent to 224.0.0.5. This is the IP address, which is a multicast address on which the updates of OSPF are sent. Just like a RIP sends it on 224.0.0.9, then EIGRP sends it on 224.0.0.10, and OSPF sends it on 224.0.0.5. You need to take that into the consideration. Okay, these three are different IP address on which the dynamic routing protocol actually sends the updates on. Make sense? And it also works based on the triggered updates. Works on triggered updates like EIGRP itself. It doesn't exchange the routing table every 30 seconds like REP. It is only going to send the update if there is any change in the network. And that's what we call as triggered updates, about which we have discussed in detail into the EIGRP section. Make sense? That's some of the characteristics. And then after that, as I told you, that it sends uh, hellos and updates and all on a specific address. But the hello also has a timer. So hello time in OSPF is 10 seconds, and dead time in OSPF is 40 seconds, which means that if, like, in order to maintain the link between the R1 and R2, both of these routers needs to exchange hello messages every 10 seconds. If the routers do not get hello message for 40 seconds, then they will kind of assume that the link is no longer up, and they will remove the routes that has been learned from that particular neighbor. Okay, and they will assume that the neighborship is broken down. You understand that? So that's what the timers are. These are, however, the default timers, and you can change those timers as well in EIGRP and in OSPF. Okay, but nobody really changes it because you really need to be good. You really need to be good enough in order to understand that how these protocols actually works according to the timer. Make sense? Then it also introduces concept of areas for the better management, which means that just like we had autonomous system numbers in EIGRP, right? So in OSPF, you're gonna have areas, different areas over here, which means if you have a couple of routers, like you have R1, then you have R2, then you have R3, and all of these are in, let's say, area 0. And then if you have R4, and then R5, and then R6, and all of these are in, let's say, area 10, then you can actually make different areas communicate with each other, but still they will be part of different area itself. Okay, now we're going to talk about how these area systems actually work, okay, for the better management perspective, so that you can scale in a great manner possible by taking help of areas here. So I hope you understand that particular concept as well, that how areas actually work here. And there are different types of areas as well that are designated in terms of like creating the OSPF neighbor. So yeah, that's one of the things that it introduces the concept of areas for the better management purpose. Okay, and yeah, you can say these are different uh, characteristics of how OSPF actually works, and I hope you understand all of these characteristics. Pretty basic one. Now, what we're gonna see is we're gonna discuss about how OSPF actually builds up the neighborship, just like what we discussed in EIGRP, that how EIGRP neighborship is built. We are going to talk about how OSPF neighborship is built over here now. Okay, so for that, I'm gonna take again the same router. Let's say we have R1 here, then we have an R2 here, and we are discussing about OSPF neighborship process. Good. So in this OSPF neighborship process, you have this R1 and you have that R2, and both of them are connected with this 12000 slash 24, where dot 1 is here and dot 2 is here. Make sense? As soon as you configure OSPF onto the routers, then the thing is going to be same here. But there are certain OSPF stages that you actually need to know. So when the OSPF is just configured and there is no network that has been advertised, then there is a state of the OSPF which is called as down state. And as you turn on the interface and advertise the networks, then that particular state changes from down to something called init, that OSPF has been initiated. Make sense? And once it reaches out into the init state, then both the routers will start sending the traffic. Okay, they will say hello on a multicast address that's going to be 224.0.0.5. And then R2 is also going to send hello message saying 224.0.0.5. And just like EIGRP as well, there are certain OSPF neighborship parameters as well that actually needs to be matched. So the first parameter over here is that both the routers needs to be again in same subnet. Okay, then the second parameter is their area number that you're going to configure also needs to be same. So they should be member of same area. And then the third parameter over there is they should also have same hello and dead timer. You understand that? In EIGRP, the third parameter is that they should have same K values, but there is no concept of K values in OSPF. That's why it considers that the timers, which are hello and dead timer, needs to be same on both the sides. And this is not a criteria in EIGRP. You can have different timers in your EIGRP and still you can become neighbor, but that's not going to happen in OSPF. Do you understand that? So after matching these, you can say parameters, then you will become neighbors. And then OSPF also maintains something called OSPF tables. And the very first table is of course called neighbor table. And the information about that neighbor is going to be installed into the neighbor table of the OSPF. Make sense? And then the state will be called as something like two-way state. It means that the exchange of the hello packets are done and now the neighborship has been formed. Okay, so you will become in two-way state. Then the next state is basically called as X start, which means they need to start the exchange of the routing table because both of the routers must have advertised some of the networks, and these networks needs to be exchanged between the OSPF neighbors. Now the question over here is who will do the exchange first? Okay, Is it gonna be, is it like, is R1 going to send the update first, or is R2 going to send the update first? And this particular thing is actually decided by something that is called as, let's say, just a minute. So this is something that is actually decided by a thing called router ID. Okay, now what is this router ID? So there are certain priorities that how router ID can be figured out, and there is, you can say, there will always be a router ID configured for a router that actually participates in OSPF. Okay, so the first priority is given to manual router ID. It can also be configured manually, so you can have a manual router ID there. If the router ID is not configured manually onto the router, then the router will automatically choose the router ID, and it will give the second preference to the highest loopback interface IP, or the highest loopback IP. And even if there is no loopback that is configured onto the router, then the third priority will be given to the highest active physical IP. You understand that? Which means that, consider that there is a router which has this as an interface, this as an interface, and this as an interface. And you have an IP address of 10.1.1.1, which is FA0/0. Then you have 172.16.0.1, which is loopback 10. And then you have 192.168.1.1, which is FA1/0. So for this router, what is going to be the router ID? Can you guess that? Yeah, of course. So the highest, because there is no manually configured router ID on that R1 available, right? So for the same, the second priority will be given to the highest loopback. Now, even though the physical IP address over there has the highest IP configured amongst all of them, but the second priority is given to the loopback interface. Okay, and that's why 172.16.0.1 becomes the router ID of that particular router. And it doesn't really matter whether you have advertised that particular network into the OSPF domain or not. It is possible that you are not using that particular network into the OSPF domain, but still your router ID will be configured, or your router ID will be assumed, which is the loopback interface IP address. Make sense? So that's how router ID is actually considered there. And we, however, in our topology are going to configure the router ID manually, so no need to worry about that now. But yeah, if we look at the topology that we have, then R1 and R2, both of them have the both of them have the IP address, which is 12.0.0.1 and 12.0.0.2. Okay. And if you look at that, then 12.0.0.2 becomes the highest active physical IP address. And that's why R2 is going to be the one who will actually initiate the routing update. Make sense? So loopback interface, as I told you, that it's just a normal interface that we're going to see how we can configure that loopback interface. Okay, it's just like a physical interface, but it physically doesn't exist. So you can go onto that particular router, you can just say interface loopback 10, and a new virtual loopback interface will be created, and you can assign it an IP address. Okay, so that particular IP address can be verified by running a do show IP interface brief command into your router, and that should solve your purpose. And then over here, if you look at X star, then based on the router ID, because R2 has a higher router ID, router IP address, that's why it's going to become the router ID of choice. And then R2 is going to exchange the routing table by saying, here is my routing table, right? And then R1 will basically give an acknowledgement to that, and R1 will exchange its routing table as well, saying here is my routing table, and then R2 will basically acknowledge to that as well. You understand that? Now, here is a major difference between EIGRP and OSPF. We saw how EIGRP and OSPF actually differs in a way of how they exchange the routes or the number of routes that are available into the topology. Okay, so assume that you again have R1, and then you have R2, and then you have R3, and then you have R4, and then you just want to reach out to R5. And as I told you in the yesterday's example, that R2 has around 2 routes, R3 has around 3 routes, and R4 has around 5 routes. And these are basically OSPF neighbors. Okay, so when we consider them as OSPF neighbors, then in EIGRP, the neighbors will just give their best route that is available to the destination. But OSPF neighbors will give all the route that they know about. So R2 is going to give the 2 routes, R3 is going to give the 3 routes that it knows about, and R4 again is going to provide the 5 routes that it knows about to reach out to the destination. They are not going to give only the best route, but they are going to give all the routes to the neighbor. And these routes are basically going to be inserted into the second table of OSPF, which is called as database table. Makes sense? So this route is going to be established or is going to be stored into the database table, and then the calculation will be done, and the state will actually be called something as loading. Okay, now the state will actually be called something as exchange, which means the routing table has been exchanged when the routes are placed into the database table. And then the next stage is going to be something called loading. And what do we mean by loading? Loading means the process of selecting the best route from the total available routes into the database table and then placing the best route that is available into the routing table or route table. So there are going to be almost 10 routes into the database table, and out of that 10, only one route will be going into the routing table. And that process is basically done in the loading state. And once it is done, then your topology reach out to a state called full. Okay, so when it reaches out to the full, it means that the network has been converged, and you can actually send data to the neighbors or through the neighbors to the destination network that is available. Do you understand how it works? So this full is going to have that routing table over there. Make sense? Yeah, so go ahead and try this particular lab and see if it works for you. Okay, let's move on with the next thing. I hope you can hear me and I hope you can see my screen. Perfect. Now so in this section we are going to discuss about the advancements of OSPF and how it actually works. So we will first investigate different tables that are available in OSPF, like we talked about neighbor table, we talked about the database table, and we talked about routing table as well. So these tables can actually be viewed over here by using commands like enable conf t and saying do show IP OSPF neighbors. And when you use that, you will see that the neighbor ID is 2.2.2.2, right? Then you see the state over there, the dead time there, then the address there. You see, so how it works is the dead time actually spans from 40 to 31, 40 to 31, and every time it receives a new hello, every 10 seconds it restarts or it goes back to 40 seconds. So the counter resets to 40 and it again starts till 31, 36, 34, 33, 32, 30. You receive a new hello, again starts from 40. Make sense what I'm talking about? So if this particular dead time reaches out to 00 from 40, it means that it's been 40 seconds that your link has not received or your router have not received the hello message from the neighbor, and then the neighborship will go down. You understand that? So the hello time and dead time is there in order to help you to understand how it actually works there. And you can see that your neighbor is being identified with router ID 2.2.2.2. Okay, and the address over there is 192.168.3.2 as well, which is the neighbor's interface address with which you are connected. Then you can also check the routing or the database table that's there, which can be viewed by saying do show IP OSP of database. And this is the database that you have. Okay. Now, to study OSP of database, it is not that easy as compared to the database, or you can say link of EIGRP's topology table. OSPF's database table is quite difficult to understand. Okay, and this is something that you will learn in CCNP when you will investigate OSPF in a deeper manner then, because there are a lot of aspects that are available. You need to learn about LSU, you need to learn about LSR, you need to learn about link state advertisements and so on. But yeah, you can get to know about that you can check the OSPF database like this. Okay, then after that you can just like, yeah, in order to get to know about it, then you can perform do show IP route here. And in the do show IP route, you will see a route there that actually specifies. If you just want to check the OSPF routes, then you can perform a command like this as well, do show IP OSPF route. And it will only show you do show IP. Oh, sorry. So what you can do is show IP OSPF, and then okay, that's something that is available for EIGRP, not OSPF. But yeah, in order to check the routing table, you can perform show IP route directly there, and you will see that the route is present over there with the OSPF thing. Make sense? So these are different, I would say, tables that are available with which you can get to know about the information. And then after that, the major thing that you need to understand over here is how the router ID works. So you see, if I use, or if I'm using my router ID over here, that says actually or that is actually 1.1.1.1 here, and then my router ID is 2.2.2.2. Okay, in that particular scenario, what happens is, if and only if the router ID do not matches with each other, then and then only they will become neighbors. Because what happens, the routers store the information about their neighbors with the name of the router ID itself. Okay, as I showed you, that you can check over here, show IP OSP of neighbor. There you go, 2222. So you or the router is not storing the information about the neighbor with the help of some IP address or so, however, that contains the information about that IP, but it identifies the neighbor with the help of the router ID itself. Okay, and when if you end up configuring the router ID that is same there, like instead of using 2222, you are also using over here 1.1.1.1, then this kind of becomes a mismatch there, which means the router ID are not different, and that's why it gets hard for that to identify how your router ID is being performed. Make sense? So that's why you need to keep the router ID different, and I hope that makes sense to you. Yeah. As so I'm saying, yeah, over here, if you want to check just the OSPF route, the command I believe is not show IP OSPF route, it's show IP route OSPF as mentioned. Yeah. So this is the routing table for the specific OSPF route that you can learn. Sounds good. So that's basic characteristics. Now, another factor that we actually need to understand over here is how OSPF areas work. The most important thing over here is OSPF areas. So when we talk about OSPF areas, then there are, I would say, two type of areas that we have, or three type of areas. Yeah. The first type of area that you have is normal area, and the second type of area that you have is called as backbone area. What is this normal area and what is this backbone area? In order to understand this normal and backbone area, when I say that my R1 and my R2 is participating in common areas, be it 10, be it 20, be it 30, be it any number. And the number can be actually with anything between a given range. But when we talk about it, you can understand that if I have a router over here, and then if I have a router over here as well, and possible that I have advertised my route as part of area 10, and then I have advertised my route as part of area 20 on R2. So do you see that the network that is actually being advertised on R1 and R2 are part of different areas there. So what would happen in that case? In this scenario, then the routers will not be able to communicate with each other because they are participating into different areas. Make sense? If I'm using, and usually this particular backbone area there is called as area 0. Area 0 is dedicated as something called backbone area. Okay? And normal area is anything except area 0. So all your area 1, 2, 3, 4, 5, 6, 10, 20, 30, whatever you get, it's all area, it's all like a normal area. It's treated like a normal area. And your normal areas cannot communicate together until unless they are directly or indirectly connected with backbone area. Do you understand what I'm trying to say here? I'll explain that again to you. So consider one more thing here, that instead of having this topology, let's say something like this. So you have your R1, and then you have your R2, and then you have your R3 and your R4 connected with it, and then you have your R5 and R6. This is your topology. Now let's say that the network that you're using over here is 12.0.0.0. Oops, sorry about that. I'll again draw that. R3 has R4. Yeah. So as I was talking about, that if you have your R1 and then you have your R2 connected there, and with that you have R3 and R4 connected, with which you have R5 and R6. This is your topology that you have. Now in this case, let's consider that R1 and R2 has a network of 12.0.0.0. R1 and R3 has a network of 13.0.0.0. R2 and R4 has a network which is common between 24.0.0.0, and R3 R5 has 35.0.0.0, and R4 and R6 has 46.0.0.0. Okay, and every router over there has certain, you can say, fast Ethernet network that is connected with them. So if I take a scenario in which R1 and R2 are sharing a common area, which is area 0, then the networks which actually will be advertised into the area 0 will be able to communicate together. Do you have any question over here? I think you're good over there, right? That whenever you advertise a network in a common network in a common area, that particular networks will be able to communicate together. Then after that, consider that this R3 is actually participating into another area. Let's say that is area number 10. Okay. And then this R4 is also participating in another area. Let's call it area number. Okay. Sorry about that. Yeah. So this R4 is participating in area number, you can say 20. So R1 is in 10 and R2, R3 and R5 are advertising their networks into area number 10, and R4 and R6 is actually participating into or actually advertising the networks into area number 20. And then there is another link over here. So will A10 or will area 10 and area 20 would they be able to communicate together? They will not be able to communicate together, right? Now in that case, what would happen if I create another link and I connect them with that particular link like this? Now if I connect this R3 with R4, what would happen in that case? Will they be able to communicate together? In that case as well, they won't be able to communicate. So the common matter over here or the common factor over here is that your different areas, understand this pretty well, different areas can only communicate when they are directly or indirectly connected to area 0. You understand that? It means that different areas can only communicate when they are directly or indirectly connected to area 0. For example, if I create a scenario in which that I have a router that actually advertises all of its routes into, like, it has around 3 networks. Okay, this is 10, that's 20, that's 30, and that particular router is connected with another router which is R2 with 20 network, and then your R3 is over here that actually has a network called 40. Now as a matter of fact over here, both of this 10 network is actually advertised in area 0. You understand that? And then this 20 network is advertised in area number 10. Now tell me one thing, that will this R2 be able to communicate to a network called 40? It will be able to communicate with the network that is connected to R3. Makes sense? 40 is basically a network that's 40,000. And why is that? Because it will be able to communicate with it because R2 is trying to communicate with 40.0, but it will be able to communicate there because R2 is connected to a network which is also a part of an area or a router that participates in area 0, which means that different area 10 and area 0 can communicate only because area 10 is connected to a router which also is a part of area 0. quite complicated it is, but yeah, you need to understand it in a way that whenever you have a network that is advertised in not in backbone area, not in area 0, but your router is able to communicate with a router who has advertised that particular router's networks into area 0. So as R2 can communicate with R1, right? Do you understand that? R2 doesn't have any area route advertised in area 0, but R2 can communicate with router 1. Do you understand that? R2 can communicate with R1, and R1 has one of its network advertised in area 0. Makes sense? That's why it will be able to communicate with any area that is connected or any area that is advertised in the area 0. Makes sense? This is actually how it works here. And now let's say, as we can take an example, let's say there is another router that's called R4, and that R4 has another area called area number 20. You get that? So in that case, R4 is connected to a router which is not majorly a part of R3 there. So for that reason only, R4 will not be able to communicate with R3, because R4 is not connected to either area 0, or also it is not connected to any router that actually has advertised their route into the router 0 or into the area 0. Make sense? So every single router needs to have direct or indirect connection with area 0 in order to make the network advertise, or in order to make the area communicate with that particular router. Make sense? You'll understand it in a better way when I execute this scenario. Okay, so let's go and see how it will kind of affect uh, in a real-time topological scenario. So what I'll do, I'll kind of remove, I will kind of, yeah, let's say, I will delete this, or you can say, I will change this to area 0. Now, instead of this, we can do one thing. That I'm going to remove the routes that are advertised in area 10 and 20. Okay, so on R1 you can see that show IP route, or do show IP route, and you can see over here that when I perform do show run to check the running configuration, you can check your router OSPF configuration that I've advertised both the routes 1.0 and 3.0 into area 10. Now what I'm going to do is I am going to advertise, because if I check now if my PCs or if my device will be able to communicate with the other devices that are situated there, then you can see I select a packet, send traffic from here to here. The first packet will be failed, and then it will go successful. If I try to send traffic from here to here, it will first will be fail and then successful. So the communication is working between area 10 as of now. This is area number 10. However, I have renamed it to area 0, but it is area number 10. Now what I'm going to do, I'm going to add another router. And in that particular router, I'm going to advertise that network. Yeah, I'm going to add this router. Then I will add another switch there, and then I will add another PC there, and then the connectivity. You get that? And this particular router is going to participate into something called cool. So this is still your area number 10, and then this over here becomes your area number 20. Good. Now over here, the network that we're gonna have, again, I'm gonna give it as 192.168.5.0/24, and then I will give it as 192.168.6.0/24. Okay, 192.168.5.0 and 192.168.6.0 in that case. So I'm going to build up this IP configuration here and see how it works. So I'm going to go on to the R3, go to the CLI, say no, enable, config, interface, FA0/0, no shutdown, IP address 192.168.3.1. Oh no, we're going to have 6.1, right? Then IPDSCP pool B or C and network 192.168.6.0 along with the subnet mask, and then default router of 192.168.6.1, and then we take an exit there, go to interface SE2/0, no shutdown, and say IP address 192.168.5.2 along with the subnet mask and take an exit. Right? If you go and check, we have 6.1 configured on the FA0/0 and we have 5.2 configured on the SE2/0. And I'm just going to add 5.1 onto the SE3/0 of this R2. So I'm going to go on that, say enable config interface SE3/0, no shutdown, and then IP address 192.168.5.2 along with that. Oh, sorry, it needs to be 5.1 here, right? Otherwise, there will be the same IP address. So that's how the IP config is. So we have now 3.2 and 5.1 there, and then we have 192.168.6.1 and 5.2 there. Now what I'm going to do is I'm going to advertise both the routes, which is 6.0 and 5.0 on R3 as a part of area 20. Okay, so I'll go over here, I'll say host name is R3, router OSP of 3, let's say, router ID 3.3.3.3, and then I'd say network 192.168.5.0 area 20, and then I will also advertise this as 6.0 area 20. Okay, then after advertising both the networks into area number 20, I'm going to advertise 5.0 of this particular router into the same OSPF process but in different area. So if I check the current configuration and if I say do show run pipe section router OSPF, it will just show me the running configuration of the OSPF. There you go. So I'm using process number 2, okay, and I'll go in that particular process saying router OSPF2, and then I would say network 192.168.5.0.0.0.255 area 20. And now if I check You see, a new neighbor adjacency has been formed, and you can verify that by saying do show IP OSP of neighbor, that there a router, an area is a neighbor is 1111, and there is another neighbor called 3333. You get that? And then in that particular case, this particular router, which is R3, also has a neighbor. Do show IP OSP of neighbor. There you go. 2222. Make sense? Now, if I go on R2 and if I check that, do show IP route. This particular router has the knowledge of 1.0, which is basically a route that has been received from R1, right? And it also has a route that's called 6.0, which is received from a router called R3. But R1 is connected with R2 via area number 10, and R3 is connected with R2 via area number 20. So if I go and try to communicate with here and here, let's see what happens. IP config. I'll get the IP addresses on these PCs. There you go. And on to the other PC, desktop, IP config, and DHCP. There you go. The IP is configured, and if I go and check now, and if I try to send traffic from here to here, the first packet failed, second also failed, so failed. You see, it's being failed. And why is that? Because when I go into R2 and if I check that, do show IP route, do show run section router OSPF, then you can check that the route, which is 192.168.2.0, which is actually the route over here. I have advertised this particular route as area number 10. Makes sense? And I have not advertised that particular route as area number 20. So even though the router has the information about the source network and about the destination network, even then as well, the traffic is not being forwarded onto that particular destination network. Why is that? Because that route is not part of that particular area. Now, what happens if I do something like this? If I try to ping directly from the router by saying do ping 192.168.6.2, then I'm able to ping from the router to the end PC. So from here to here, the communication is working, but from PC to PC, the communication is not working. Okay. Now, what happens? So if I kind of go ahead and if I add another network here with that particular router, let's say I add a switch there, 2960, and I add a PC there. I'll just add a single PC here, and then if I try to connect with that particular PC, okay, and then let's say I create a network 192.168.7.0/24, okay, and in that scenario, I provide the IP addressing scheme to that. So this is 7.0 here. So I go on to the R2 and I configure FA1/0 with that thing. This is R2 interface FA1/0, no shutdown, IP address 192.168.7.1 along with 255.255.255.0 IP DHCP pool. Let's say B there, C there, network 192.168.7.0 along with 255.255.255.0 default 192.168.7.1 and take an exit. Okay, then I'll go on to the PC. That's fine. I can have the pool number C as well because C is here and C is here. So locally, that's again local significance. So I go on to the PC and then desktop. and then go to DHCP. There you go. DHCP request successful. So you can check that it's working there. And now what I'm gonna do is I am going to advertise my newly created network as a member of area number 20. So I say router OSPF, what that thing was. So I say do show run section router OSPF. Yeah, OSPF number 2. So I say router OSPF 2 and then say network 192.168 uh, 7 or yeah 7.0 and the wildcard mask will be 0.00255 and area number 20. When I advertise this route, you can check that there is a new route that has been advertised now. And after that, do show IP OSPF neighbor or do show IP OSPF or do show IP route. There is no change into the local route. There is just a new directly connected route that has been added. But if I now check my other router, which is R3, do show IP route, then you have a new route that has been added, which is 7.0. Make sense? But whatever route on, be it on, or whatever routes that are there, which are advertised as member of area number 10, okay, be it like 2.0 or be it 3.0 or be it even 1.0, those routes are not exchanged to R3 because R3 is not participating into that particular area. But R2 is participating in area number 10 and also in area number 20. That's why when I try to send traffic from here to here, the first packet will fail. There you go, successful. The ARP was already done there. Make sense? So the communication between here and here is possible. And the communication between here and here is also possible. You understand that? And that's how normal areas actually behave with each other. Okay? This is all normal area. We're not talking about backbone area yet. Cool. So that's kind of an understanding of how normal areas actually work. You cannot make different areas, be it area 10, 20, 30, 40. They cannot actually communicate with each other, even though you have advertised the traffic, you have advertised the network under the same OSPF process. Okay, yeah. Somewhat like VLAN, but not completely like VLAN. There is a bunch of other things that are available in OSPF that you will learn in professional studies. But yeah, this is just an overview of how areas actually work. So go ahead, try this particular thing, and then after that, we'll see how backbone area comes into play in that particular scenario. Okay, try this lab and let me know when you're done. So in this section, we're going to discuss about the area 0 and its characteristics, that how it can actually communicate when you make it part of area 0 or so. So what we are going to do here now is we're going to create another network in our scenario, and we are kind of going to make this area 10 and area 20 communicate with each other. Okay, and I'll show you how you can actually do that. So I'm gonna drag this particular topology down, and we are going to create another sort of network there by placing a router. Let's say I drag a router there, and then in that particular router, what I do is connect those routers with something like this. Okay, I take a cable there and connect it with this, and I take another cable and connect it there. You get that? Now over here you can see that the network that we are going to create in that particular scenario is that you can actually get rid of this network which you have here, So what I'm gonna do, I'm gonna delete this network completely, and I will also delete this router here. Make sense? And I will also delete this area and this area. So we don't have these networks anymore, and we just have this plain network. And in this scenario, we are going to create a network which is 192.168.1.0 is here, 192.168.6.0 is here, and then we're going to create another network. Let's say the network between this is going to be 192.168.2.0/24 and 192.168.3.0/24. Okay, that's how the network is going to be. So what I'll do, I'll remove the OSPF configuration from this router and from this router. So I'm gonna go onto this router here, say enable config, and I can check do show run section router OSPF. We are running router OSPF 1 here. So we say no router OSPF 1, and you can check do show IP OSPF, oh sorry, do show run section router OSPF. There you go, nothing's there. Same way, we're going to remove the OSPF configuration from the other router that we have. Enable config do show run section router OSPF. There you go, no OSPF run. So there's OSPF process 3. So I'll say no router OSPF 3. And that's how you make it clean. So as of now, there is no OSPF configuration that is done in any of our routers. There is just IP configuration that has been done, out of which we are not using SE2/0, but our SE2/0 is configured with 5.2. So I'm going to remove that particular configuration from there, and I'm going to keep the 6.0 configuration because we still have that network in our scenario. You get that? So for removing the configuration of SE2/0, I can simply go to config and I can use a command called default space SE2/0 or default interface SE2/0. So it brings down the configuration to the default configuration itself. Okay. So when I say default interface SE2/0, what it does, it removes all the configuration that you've done. There you go. SE2/0 is now went to state down, and then there is no IP address that is configured. You get that? Just like that, I'm going on to the first router as well, and there we have SE2/0 as well configured. I'm also going to remove that particular configuration from there. Okay, yeah, it will work to FA0/0 interface, big interface, any interface that's there. So I'm gonna go on my R1 and I'm gonna say default interface SE2/0, and there you go. We have removed the configuration of that particular interface as well. And now we're gonna configure our serial interfaces that we have. So I'm gonna go on R1 and configure 2.1 here, 2.2 here, 3.1 here, and 3.2 here. So that's my R1 config interface SE3/0, no shutdown, IP address 192.168.3.1. Oh, that's 2.1, I believe. Yeah, 2.1, and then this submit marks. There you go. SE3/0 has been configured with 2.1. Then I'm gonna go on to the next router, which is R3, and configure it with 3.2 on the SE3/0. So that's our R3 interface SE3/0, no shutdown, IP address 192.168.2 space 255.255.255.0. So we have configured IP address 3.2 on our R3's interface that is connected over there. And then we will name this router as R2, and we are going to make this particular router as a member of area 0. So I'm going to go and configure 2.2 and 3.1 over here. Okay, or yeah, 2.2 and 3.1. Let's first check Yeah, 2.1 is here and 3.2. Okay. So I'm going to go on this router and configure it with the dedicated or desired IP addresses. I'm going to say enable config host name R2 interface SE2/0 no shutdown IP address 192.168.2.2 along with the subnet mask, and then interface SE3/0 no shutdown with IP address 192.168.3.1 along with the subnet mask and exit. And there you go. The links are up and the IP or the topology is working all good. Now we're gonna make the partitions in a way that how the areas will actually be working here. So I'm gonna select the color for our area 0. That's gonna be our area 0. And then we're gonna have our area 10, which is this. And then we're gonna have our area 20, which is this. Okay, so that's our oops. So that's our area 20. This is our area 10, and that is our area number 0. Sounds good? Now we just need to go into every area and we need to advertise the network for a dedicated area number that we have. So I'm going to go on R1, then I'm going to create an area process number 1 and advertise 2.0 into area 0 and 1.0 into area number 10. Make sense? For that, I open up our for that I open up our R1 and I say router OSPF1 router ID 1111 and then say network 192.168.1.0.0.0.255 area 0, and then I'm gonna advertise 192, or you can say network 192.168.2.0 in 0.0.0.255 area number. Okay, I did the wrong thing. So I needed to advertise 1.0 into area 10, right? So I remove that particular route by using no command. Yeah. So I will remove that route and I will advertise it by using area number 10. And then I will advertise this particular route, which is 2.0 in area number 0. There. That's the correct way of implementing it, right? So that's what we need to do over here on R1. Then I'll go on R3 and do the same thing, that advertise 6.0 into area number 20 and 3.0 into area number 0 again. So there you go. On this is our R2, and that's our R3. So over here I'm gonna say router OSPF3, router ID 3333, and then I say network 192.168.3.0.0.0.355 or 255, and then area 20. Oh, sorry, area 0, and then network 192.168.6.0 area 20. Correct? That's how the configuration needs to be done on R3. So both of the networks are advertised into their respective areas. Then I'm go on to the middle router, which is R2. And then over here, I'm gonna advertise both the routes that I have, or both the networks that I have as part of area 0. So I say router OSPF2, router ID 2222, network 192.168.2.0.0.0.255 area 0, and then 192, there you go. And then I say 3.0, and there will be another OSPF adjacency 192.168.3.0. There you go, another neighbor came up. Makes sense? And you can check that by saying do show IP OSPF neighbor, There you go. You have two neighbors over here. And if we check now that whether the communication, because if I look at the routing table over here, do show IP route. There you go. You have received a route update that is 192.168.1.0. Okay, there seems to be some misconfiguration on R1, but if I on R2, if I look at the routing table, the routes that you actually receive from different area will be tagged as OIA, which means OSPF route that is received from inter area. So the routes that you receive from different area is called as inter area routes. Okay, and the route that you just receive from the same area will be treated as normal OSPF route. But in our scenario, for this particular second router, the route which is 1.0 should have been an inter-area route and not an intra-area route because it's being received from area number 10. So I'm going to go on R1 and check in which area I have advertised it. You see that? I have advertised it correctly in the area 10, but let's check that. Do show run section router OSPF. And yeah, 2.0 is part of area 0 and 192.168.1.0 is part of area 10, which is correct according to my knowledge. If I again check that do show IP route, again this route should have been an OSPF inter-area route, just like you have 6.0. Anyways, if I go on to the router number 1 and check the routing table, do show IP route. There you go. You have 192.168.3.0 that is treated as so you should have had two inter-area routes there, which is 3.0 route and which is 6.0. Okay, yeah, but only 6.0 is being treated as inter-area route over here as well. If I go on to the last router, which is R3, and check do show IP route there, over here none of the routes are being treated as inter-area routes. However, it has both 1.0 and 2.0 as the OSPF routes that are being received there. But you can see that IA, which you can see over here, IA stands for OSPF inter-area routes, and normal O stands for OSPF routes. This might be one of the bug over here that you see of the packet tracer, but originally you can treat it somewhere like in the middle router, both the routes that would have been received from area number 10 and area number 20 should have been in inter-area routes. It's only showing 6.0 as the inter-area route and not showing 1.0 as inter-area route over here, but it should have been like that. So this is kind of a bug, I can say, of packet tracer. But originally, for making the concept clearer, the routes that you receive from different OSPF area are treated as OSPF inter-area routes, and they get highlighted with an IA tag along with the O tag. However, yeah, however, you can see if we check the communication whether it's being made possible or not. If I send traffic from here to here, yeah, it's going successful. So the communication is being made successful over there. But again, it's just the highlighting of packets that how the routes are being treated. So that's kind of a bug in packet tracer, I can say. But so far, in order to understand how the concept works, this is what we had to check, that how backbone area, which is area 0, connects normal areas together and how it lets you communicate between multiple areas if your areas are also connected to the backbone area some or the other way. Do you understand that concept? Perfect. So go ahead, try this particular lab into your packet tracer as well and see if it works for you. All right, guys, I believe you guys are done with the thing. And I believe you understand OSPF pretty well now. So far, that is needed in CCNA. So I would say that was actually all that we had to discuss in this particular session, and I hope you enjoyed the content. And we are pretty good with routing that we had to discuss. We discussed about all the protocols, even though in official CCNA curriculum, the RIP and EIGRP has been removed now, and there is just OSPF and static routing that is there. So, but in order to understand the importance and to understand OSPF, you actually need to have the knowledge of how RIP and EIGRP works so that you can compare it. And yeah, for the remaining sessions, however, I would like to notify you that we are just gonna have another 2 sessions next week, because from the following week, which is like next to next week, I have an important assignment to take up. So the remaining part, which is switching, will be done in one class, and then access control list, network address translation, security, and automation will be discussed in another class. So probably we're gonna have an extended class in the next weekend, because we have just 2 sessions that I can afford in order to have with you guys, because I have something else that I have came up to in my schedule, and I cannot ignore that. So hope you can understand that. However, we will extend the time of our session if it's needed. So yeah, so I believe that you have been that you enjoyed the session today, and I'd like to thank you for joining it. I'll see you guys next week, same time. Till then, do practice a bit, okay? Spend some time over there.
If you enjoyed the content of the video, don't forget to like and share the video and subscribe to our channel.
All right, thank you everyone. Take care of yourself. I'll see you guys next weekend. Till then, have a good weekend. Have a good weekday ahead. And yeah, thank you. Bye bye.